Hello again, everyone. Welcome back to General Chemistry. I know it's been like 3 months since the last upload, so my apologies to the 5 of you that are actually watching these videos at the time of upload. But I am back. I had my winter break, and I was a little busy with preparing students for their finals for the first semester and all that, but that's behind us now. The important thing is I'm back, and today we are going to talk about solutions for the most part, mixtures in general, but mostly about solutions. So let's get started. So first, maybe a little bit of a callback to some ideas that we covered in the very first general chemistry video. You might recall that mixtures fall into two categories: homogeneous mixtures and heterogeneous mixtures. Homogeneous versus heterogeneous. I haven't used these markers in a while, and I can see this one looks like it'll probably die today. Okay, homogeneous versus heterogeneous mixtures. And of course, what distinguishes them from each other is that homogeneous mixtures are uniform throughout, while heterogeneous mixtures are not. Homogeneous mixtures are also known as solutions, which we've dealt with quite a bit. Solutions. While heterogeneous mixtures we haven't really dealt with all that much, but yeah, heterogeneous, non-uniform. So of course, quick examples of heterogeneous mixtures are things like salads and sandwiches and basically anything where you can tell that the components are not distributed very evenly. But some heterogeneous mixtures are a little bit less obvious, such as tomato soup, for example. Tomato soup is heterogeneous because you can still see like the tiny little bits of tomato, and especially if you look around the surface of the tomato soup, if you look around the edge of the bowl, you can tell that you see this kind of a thin, almost transparent layer where you can clearly tell the water and I guess the salts in the water are separate from the tomatoey bits. But yeah, that's homogeneous versus heterogeneous. And homogeneous mixtures, also known as solutions. We've only dealt with one specific type of homogeneous solution up to this point, which is the aqueous solution. We've only dealt with aqueous solutions, or liquid solutions, in other words, but there are other types of solutions. Let me pull up this chart illustrating some of the different types. So, as you can see right there, you can have all sorts of different phases for the solution and solvent. Basically, every combination can work to produce solutions. They don't always produce solutions, but sometimes they do. So, as an example, you've got air as a solution. It's a mixture of all sorts of gases, not just oxygen and nitrogen, but we'll pretend that we just have oxygen and nitrogen for our example. So basically that's an example of a solution of a gas in a gas. You can also have a gas in a liquid. So classic example would be your soft drinks. Hydrogen in palladium, that's an example of a gas dissolved in a solid. Rubbing alcohol is a liquid dissolved in a liquid. In this case, water in, it looks like 2-propanol. We'll talk about what the 2 means much later in either video number 19 or 20. Oh, I forgot to mention that. I have finished planning out all of the videos, and it looks like We're looking at a grand total of 20 videos for the whole series, for those of you who were wondering how long this is going to be. Going back to salt water, we've already seen plenty of examples of this. Solids dissolved in liquids. Brass is a solid dissolved in a solid. And yeah, every combination you can think of, you can produce solutions. So what do we not have here? We've got gas and gas, gas and liquid, gas and solid, liquid and liquid, solid and liquid. We don't have gas and liquid. Wait, yes we do. Yes we do. Let's see, what do we not have? We don't have liquid in gas or liquid in solid, but it is possible to have that. We've got solid and liquid, solid and solid, and it should be possible to also dissolve solids in gases. I can't think of examples for all of those off the top of my head, but it is possible. Okay, so those are some different types of solutions. You really just need to kind of be aware of all the possibilities. You don't really need to know about, gas and solid solutions in that much depth, for example. But yeah, that's there just kind of as an FYI. We will still mostly be dealing with aqueous solutions. So let's talk about how solutions actually form. In the previous video, we talked about the intermolecular forces, and I did mention, if I recall correctly, something called the ion-dipole interaction. Ion-dipole interactions, which I didn't really talk about all that much. I think all I did really was mention that we would be talking about them at a later time, and that later time is now. Ion-dipole interactions. You can think of them as the fourth intermolecular force. So, ion-dipole interactions help us explain how ionic compounds dissolve in water. What about non-ionic compounds? We'll get to that. But let's take a look at this diagram over here that illustrates the process. So, in the bottom, you've got some crystal of potassium chloride. Potassium ions are in purple, chloride ions are in green. And then you've got water molecules. And what the water molecules will do, remember that they have a lot of polarity to them. So they have like a positive end and a negative end. And so the positive ends of water molecules get attracted to the negative chloride ions, while the negative ends of the water molecules get attracted to the potassium ions. And you can actually see that up near the top. So you've got right in the middle at the top is a chloride ion, and you can see like the hydrogen sides, the white parts of the water molecules are attracted to it, whereas the potassium ion to the right of it is surrounded by 4 water molecules, and it's the oxygen ends that are attracted to the potassium ion, because if you remember, the oxygen side of the water molecule is the more negative side. And yeah, basically what's happening is a crowd of water molecules get around the ions, and eventually they kind of just surround the ions and block them off from each other. Kind of like if two people were holding hands and they walked into a big crowd, they might get separated. At least that's the analogy I like to think of. So these ion-dipole interactions kind of help to explain how ionic compounds can dissolve in water. But yeah, ion-dipole interactions are considered the strongest intermolecular forces that can exist for I guess, molecular compounds, except, you know, they don't really define boiling and melting points because the ion-dipole interactions are between two different substances, two different compounds. That's actually why I left them out in the previous video. There is something that we will learn about later on in this video about how to predict the boiling and melting points of solutions, but it's not really based on the ion-dipole interactions. Those are just kind of there to help explain the dissolution process or the solvation process. Some other things. So you can dissolve alcohol in water. You can dissolve alcohol in water. You can dissolve sugar in water. You can dissolve all of these non-ionic compounds in water. Alcohol, sugar, etc. in water. Why? Simple reason. It's because of the intermolecular forces. It's because of the intermolecular forces. So the intermolecular forces don't just act between molecules of the same type, they also act between molecules of different types. They also act between molecules of different types. So I'm going to go with, let's just do methanol, since that'll have a small Lewis structure to it that's easy for me to draw. Let's take a look at methanol, which is often written as CH3OH. CH3, so a carbon connected to 3 hydrogens and then connected to an O and an H, like that. And if you want, there's the lone pairs on the oxygen. And let's see, dissolving that in water. So how does that work? Well, the alcohol exhibits hydrogen bonding because we've got a hydrogen connected to an oxygen. Remember, hydrogen bonding happens for molecules that have hydrogen connected to fluorine, oxygen, or nitrogen. So we've got some hydrogen bonding going on here, and not only do water molecules hydrogen bond with other water molecules, they can hydrogen bond with any other molecule that exhibits hydrogen bonding, such as methanol. So the positive oxygen can, the negative oxygen can interact with the positive hydrogen on another molecule, like that. Let me see, and I guess I should have drawn this a little bit better. You know what, I'll just draw a separate water molecule. Let's draw that. That way I'm not crisscrossing my lines and making this too hard to look at. And yeah, let's do some hydrogen bonding there. And yeah, there you go. So basically the same thing that happens with the ion-dipole interactions. Water molecules can gather around these methanol molecules due to hydrogen bonding and kind of surround them and block them off of other methanol molecules. Or maybe it's the methanol molecules that surround the water molecules. It depends on the ratio. In fact, when you're trying to dissolve a liquid in a liquid, it's not always clear who the solvent and who the solute is. Liquid in liquid solutions, we don't really say one liquid is soluble in another. Whoops, I almost made that a G. Liquid solutions have no clear solvent and solute. Have no clear solvent and solute. We say, instead of saying that methanol is soluble in water or that water is soluble in methanol, we simply say that methanol and water are miscible. M-I-S-C-I-B-L-E, miscible. They dissolve in each other. So you could argue, based on the ratios, if you've got like a drop of alcohol in a bucket of water, then you could argue that the alcohol is the solute while the water is the solvent. And of course, if you reverse the situation, a drop of water in a bucket of alcohol, then you can say alcohol is the solvent while water is the solute. But in a lot of cases, it's not entirely clear. In a lot of cases, it's not entirely clear who the solvent and solute are, so we simply say that they're miscible. They dissolve in each other. Okay, what's another example I could give? So, alcohol and sugar exhibit hydrogen bonding, and that's why they can interact with water. But polar substances can also dissolve in water pretty well. Polar substances dissolve pretty well in water. So let me see, which color should I use? Let's go with the dark green, and let's do it over here. What's an example of a polar substance I can dissolve in water? This shouldn't be too hard to come up with. Let's do... I don't want to go with HCl. That's the one that's coming to my mind right now, but I want something different. You know what? Let's do CH3Cl, also known as chloromethane. Don't worry, you'll learn these naming rules when we get to organic chemistry, which I've decided to make the second to last video instead of the last for reasons that will be explained in the 20th video, for those of you that are actually going to watch it. But yeah, let's take a look at chloromethane, CH3Cl. So this molecule is polar. The carbon-hydrogen bonds aren't very polar, but the carbon-chlorine bond has a pretty significant dipole moment from the carbon towards the chlorine. The chlorine has way more electronegativity than carbon. So because of polarity, again, you can have interactions between these molecules and water molecules. So let's see, I guess I would, put the hydrogen closer to the chlorine like that. And maybe let's draw another one over there. And the partially negative chlorine will attract the partially positive hydrogens in water. I guess there's going to be a partial positive charge on the carbon there, and maybe some of the oxygen ends of some water molecules will be attracted over to here. So there's another water molecule with that bond looks way too short, but you get what I'm trying to draw. So let me see, I guess I should label that as partially negative. Same thing for these. So water molecules can be attracted to polar molecules because any hydrogen bonding molecule is also a polar molecule. So they can have these dipole-dipole interactions, which allow for the same effect as the ion dipole interactions and the hydrogen bonding interactions. Same idea. The water molecules get attracted to these polar molecules. They surround them. They isolate them from other molecules of the same type. And so these polar molecules get scattered throughout the water. One thing that doesn't work, one thing that doesn't dissolve very well in water is a compound that has no polarity whatsoever. So if I went with, and I guess I'll fit it into this tiny little corner. Let's say I went with, let's say I went with oil, and I don't really know the structure of oil, but I can tell you that oil is a compound made of non-polar molecules. Oil does not dissolve in water. And you can try this at home if you've never seen it before. Oil doesn't dissolve in water. Oil is a completely non-polar substance. It doesn't do dipole-dipole interactions or hydrogen bonding, and it's definitely not ionic. There's not much of a way for the water molecules to get around the oil molecules and separate them off from each other. And because of that, an idea emerges, this phrase that chemists like to repeat over and over again. They say, I guess I'll write it up here, they say, like dissolves like. Like dissolves like. Which is to say, polar things dissolve in other polar things, and non-polar things dissolve in other non-polar things. Even though oil doesn't dissolve really well in water, and water doesn't dissolve really well in oil, other non-polar substances do dissolve pretty well in oil. So basically, any fat-soluble vitamin is going to be a non-polar substance that dissolves pretty well in oil and other fats, while water-soluble vitamins, well, they dissolve well in water and not so much in oils. That's why they're called water-soluble and fat-soluble vitamins. Maybe you didn't hear about that before, but you've heard it now. In case you hear about that in your health class, you heard it here first. What are some other examples? Non-polar substances. I guess we could do chloroform. No, wait. Chloroform is... Why am I blanking on its formula right now? It's either CH3Cl or CHCl3. No, I'm pretty sure it's CH3Cl, chloroform. Okay, so that's not... that's a polar substance, so let me think. Carbon tetrachloride, CCl4. CCl4 is a non-polar molecule overall. Doesn't dissolve well in water, but does dissolve pretty well in oil and other non-polar solvents. Maybe I rambled on for a bit too much on that, but there you go. Like dissolves like. So ionic, hydrogen bonding, and polar molecules in general can dissolve pretty well in water, and everything else can probably dissolve pretty well in oil, but it's never a guarantee. There are some ionic compounds that don't dissolve in water. You might remember from, I think it was video number 4, you might remember the solubility guidelines that help us predict the solubilities of different compounds. And you might remember that most carbonates are not very soluble. Calcium carbonate is an example of that. You can find calcium carbonate in chalk, but you can also find calcium carbonate in something that you probably have more access to. You can probably find calcium carbonate in Tums. You can probably find calcium carbonate in Tums. In fact, I'm pretty sure that's the active ingredient. Yep. I don't know if you can read that very clearly. Yeah, if I hold it too close to the camera, I think the focus isn't going to allow you to see it. But if you believe me, active ingredient per tablet is calcium carbonate. So yeah, you can take one of these and crush it and try to dissolve it in water. It's not going to work. It is not going to work. Calcium carbonate is insoluble in water. Oh, and I guess you can also find calcium carbonate in limestone. So that's a thing too. Calcium carbonate is insoluble in water, despite being an ionic compound. Of course, soluble is a relative concept. We'll talk about that later in the video. When we say insoluble, what we really mean is that it has very, very, very low solubility. There is a tiny amount of calcium carbonate that will dissolve in water, but most of it will stay undissolved. And yeah, there is a reason for this. It has more to do with thermodynamics, which will be, I think video number 17. Let me check my cards real quick. I think I have it already planned out. No, that's video number 16. So we'll talk about thermodynamics in more depth around then. But for now, what I want you to know, even though you can't exactly make predictions based off of this, what I want you to know is that the change in the energy that's associated with the solvation process or dissolution process, the process of dissolving things. The energy change is different for different compounds, and that has a role to play in how soluble something can be. So let me pull up this diagram, I guess we'll call it. In this diagram, what you see in the middle is the solute in blue and the solvent in, I guess I'll call that red. It's kind of orange. I'll call it red. But yeah, so you've got the solute and solvent just on their own, connected pretty well. I guess those are supposed to represent either a liquid or a solid, but we'll pretend that the solvent is liquid and the solute is solid for ease of understanding and for intuition's sake. And yeah, so in the middle you see the solute particles are pretty well bonded to each other, and the solvent particles are also pretty well connected to each other via some sort of intermolecular force. Or maybe in the case of the solute, just electrostatic forces. I'm imagining it's ionic. And if you look to the far left and far right, you see the solute being separated. So the particles are separated from each other, which requires energy. Same thing for the solvent. The solvent particles, whatever interaction exists between them gets broken, so they get split up from each other. And then both of those get mixed together, and at the very bottom you see the solute particles spread out amongst the solvent particles. So new interactions basically start, is the right word forming? No, start appearing between the solvent and solute particles. And there's energy associated with this. So if you take, whether they're the solvent or the solute particles, if you break them up like this, then you're breaking some sort of bond or some sort of interaction between these, which requires energy. This requires energy and is therefore endothermic. There's a term you probably haven't heard in a while. Endothermic, requires heat, absorbs heat, or just energy in general. Maybe it's electricity for all we know. On the other hand, the reverse process, so if I have some, I guess I reversed the colors here, didn't I? You know what? No, I'll stay consistent with what they had. So I'll use this reddish orange for the solvent. If I mix these together, and I guess I'll draw a little plus sign between them to form, I guess I'll scatter them throughout. If I form these sorts of bonds or interactions between them, well, that's the reverse of breaking bonds or intermolecular forces. So you would expect to produce energy in that case. So this produces energy, and is therefore exothermic, and is therefore exothermic. And yeah, this is one factor, but it's not the only factor in determining whether or not something will dissolve well. Oftentimes, if the energy produced when bonding the solute and solvent is greater than the energy consumed in breaking up the solute and solvent from their own particles, oftentimes if the overall process is exothermic, that will make the process thermodynamically favorable. And because of that, it's going to be more likely to happen. It'll make a lot more sense when we actually get to the thermodynamics chapter. That being said, it's also possible to have a solution form where the overall process is endothermic, where the overall process requires energy, yet it still happens automatically without requiring any external energy. Instead, you'll just end up with a solution that gets colder as it forms. So the energy, I guess, just gets sucked out of the water or whatever your solvent is. And in that case, it's still thermodynamically favorable because of something called entropy. We will talk about that when we get to thermodynamics. But for now, just remember, a thermodynamically favorable process is a process that will occur on its own without any sort of outside help. You could imagine then that the dissolution of calcium carbonate is not very thermodynamically favorable. At least that's one of the reasons why it's not that soluble in water. And, I guess now's a good time to talk about heat of solution, or heat of dissolution, or heat of solvation, whatever you want to call it. heat of, some people call it heat of solution, some people call it heat of dissolution, the process of making the solution, and some people, rather than the word dissolution, will call it solvation, which is what I tend to do. I will usually use the word solvation instead of dissolution because I feel like it rolls off the tongue easier. But yeah, the overall energy associated with dissolving one thing in another thing, that's what's often called heat of solution. So, I don't really have a list of heats of solution right now, but let's take a look at the dissolution of something like ammonium nitrate. So ammonium nitrate, if you take, I'm going to say it starts out in the solid form, and if you dissolve it in water, then it's going to form ammonium ions in the aqueous phase and nitrate ions also in the aqueous phase. And yeah, there's going to be some sort of change in enthalpy. There's going to be some sort of delta H associated with this. And in the case of ammonium nitrate, it's actually going to decrease the overall enthalpy. So delta H is less than, wait, no. Backwards. Delta H is going to be greater than 0. It takes away energy from the water. It's an endothermic process. So yeah, this is going to be an endothermic process, so the ammonium ions and nitrate ions form when ammonium nitrate takes some heat away from the water. And there's a useful application to this, and that application is cold packs. So yeah, it's pretty self-explanatory at this point. If ammonium nitrate dissolving in water is an endothermic process, then you take your solid ammonium nitrate, put it into your cold pack, but keep it separated from the water until, the person actually wants to use their cold pack. Break whatever it is that's blocking off the water from the ammonium nitrate. Usually it'll be like some sort of thin film or seal. And yeah, break the seal, the water gets mixed with the ammonium nitrate takes energy out of the water gets cold, and there you go, you have your cold pack. Pretty simple, straightforward stuff. Of course, you can also make hand warmers if you pick a solute that produces energy when it dissolves, that heats up the water. So you can also make hand warmers, the opposite of a cold pack, if you want to. We'll see that later on after we talk about the process of crystallization, which can release a lot of energy, relatively speaking. Where do I want to go from here? I mean, I guess we could do an example involving heat of solution, but I think before examples, I want to review, we've covered this before, but I want to review the definition of electrolytes. That'll be relevant a little bit later when we talk about the properties of solutions. Let's talk about electrolytes. Okay, so what is an electrolyte? You might remember this from, I think it was video number 4. But an electrolyte is something that when dissolved in water conducts electricity really, really well. Or just conducts electricity, period. And depending on how well the electricity is conducted, you could call it either a strong electrolyte or a weak electrolyte. So right there in that chart you have a non-electrolyte, ethanol, on the far left. You've got a strong electrolyte, potassium chloride, in the middle. And then you've got a weak electrolyte, such as acetic acid, on the right. So really it depends on how well a substance dissolves, an ionic substance to be specific. Ionic substances, when dissolved, can form either strong or weak electrolytes depending on how ionic they are. And this is where we start noticing that some compounds are not all that ionic. I think I may have mentioned this before, but in the very first video we classified all substances as either being ionic or molecular. That's not entirely true. Some things are in between. Acetic acid is an example of that. We'll talk about this a little more when we get to acids and bases. But yeah, not all substances fit perfectly into the ionic or molecular category. Anyway, so what's the deal with something like potassium chloride versus acetic acid? So if I put, I don't know, 100 formula units, if I put 100 formula units of KCl in water, then what I get is 100 potassium ions plus 100 chloride ions. They all dissolve. They all break up, and that's the end of it. You end up with 200 particles that are free to move around and carry electricity over to different places depending on how you hook up the solution to whatever electrical device you want. On the other hand, if I do the same thing with acetic acid, if I put in, I guess I'll call them 100 molecules of acetic acid in water, then, whoops, forgot my space there. Then what we're gonna get, and I guess this marker's about as good as dead, then what we'll get is something very different. What we might get, for example, is 5 hydrogen ions plus 5 acetate ions. Let's see, so that's C2H3O2 negative, if I recall correctly. And you'd be left with 95 acetic acid molecules intact. Let me see. Yeah. So let's see, 95 acetic acid molecules. I guess that would be HC2H3O2 is one way of writing it. So yeah, 95 acetic acid molecules out of 100 didn't split up at all, just remained dissolved as they are. Which is fine. Acetic acid can dissolve in water while staying intact because it exhibits hydrogen bonding. If you don't believe me, here's the structure for acetic acid. CH3, COOH. So yeah, it exhibits hydrogen bonding. It's quite polar. So it can dissolve in water without having to split up into ions, but some of the acetic acid molecules do indeed split up. So that's basically what's going on with weak electrolytes. They don't split up entirely. And so you get less ions, and therefore you conduct electricity less effectively. But yeah, remember that for later. Do I want to talk about... Yeah, let's go ahead and bring it up. So, as we mentioned before, you can dissolve all sorts of things in all sorts of other things. You can dissolve not just solids in liquids or liquids in liquids, but you can also dissolve gases in liquids. And the way that gases dissolve in liquids is a little bit different from the way solids dissolve in liquids. Actually, you know what? Let's go back to this later. First, I want to talk about the solubility of solids. Yeah, we'll go back to gases, but let's talk about solids first so that we have a basis of comparison. So, in that chart over there, you can see that we have a bunch of different solids listed: sugar, potassium nitrate, sodium nitrate, and so on and so forth. They're normally solid unless, you heat them up and melt them, or you dissolve them in water. So you've got, for most of these compounds, as you increase the temperature, as you go further to the right, the solubility goes up. And here's where we need to talk about our definition of solubility. So way back in video number 4, we said that solubility was basically a simple yes or no question of, does this thing dissolve in this other thing? And the other thing was usually water. So that was solubility in a qualitative sense. Solubility can be defined in two different ways: qualitative versus quantitative. So solubility defined qualitatively versus quantitatively. Quantitatively. And I think I've hinted at it a little bit before. But yeah. So in a qualitative sense, when we talk about solubility in a qualitative sense, we're simply asking a yes or no question. Is X, maybe I should capitalize the I, is X soluble in Y? And it's just a simple yes or no question. A simple yes or no question. However, the truth is, almost everything has a little bit of solubility to it. We just say that it's insoluble if the solubility is really low, and soluble if the solubility is really high. But the truth is, everything has some level of solubility. So if we're asking about solubility in a quantitative sense, then we're asking, how much X can I dissolve in Y? How much of X can dissolve in Y? So yeah, the chart that we just had, and let me put it back up. This chart shows us the solubilities of compounds in a quantitative sense. How soluble are these things? And for most of them, in fact, all of them except for, it looks like I would call that cerium 3 sulfate at the bottom there. That's the only one whose solubility seems to go down as the temperature rises. But everything else, you see the solubility goes up, even if it's just a little bit, as the temperature of the solvent, which I imagine is water, rises. You can dissolve more sugar in hot water than you can in cold water. So if you've ever tried to dissolve as much sugar or salt in water as possible, eventually you get to a point where no matter how much you stir, no matter how much you agitate the solution, no more salt or sugar is dissolving. You could say the water is stuffed, it's at its limit. And that limit is what we call the solubility in a quantitative sense. Solubility, as you can see in that chart, is given in grams of solute per 100 grams of water. It can also be given in grams per milliliter. I know I've seen grams per 100 milliliter, which I guess is kind of what they're going with water, because at room temperature, the density of water is 1 gram per milliliter, so solubility in grams per 100 grams of water is the same as grams per 100 milliliters of water. 100 grams of water equals 100 milliliters of water at room temperature. And some of you might be asking, well, if this chart shows that the temperature of the water is changing, then that density isn't all that reliable now, is it? And you're absolutely right. But, you know, chemists kind of brush that off and approximate, and they don't worry about it unless they're preparing solutions for NASA or something like that. So don't worry about it until it's critically important. But, you know, there's solubility, typically given in grams per 100 milliliter of water or grams per 100 grams of water. I guess grams would be more consistent because they don't change as you change the temperature. And maybe that's why they drew up the chart the way they did. So let me see. Sugar at 20 degrees, it looks like I can dissolve about 200 grams of sugar in 100 grams of water. And if I raise the temperature to something like 60 degrees Celsius, it looks like I can dissolve a little over 280 grams of sugar in the same 100 grams of water. Now, what happens if I reach the limit at a high temperature and then I lower the temperature? So let's talk about the concept of saturation before we answer that question. Let's talk about the concept of saturation. Okay, so saturation occurs when you basically reach the limit on solubility, when you dissolve as much stuff in your water or whatever solvent you have as you possibly can, when you've stuffed that water to the max. So we say that a solution is unsaturated if you don't fill it to the limit. We say it's saturated if you do fill it with solute to the limit. So unsaturated, have not dissolved the maximum amount of solute. It's unsaturated if we haven't dissolved the maximum amount of solute and it's saturated if we have. It's saturated if we have dissolved the maximum amount of solute. So I guess I'll say solute content is maxed out to keep it short. Solute content is maxed out. We've put in the maximum amount of solute we can. We've maxed it out. There is a third type of solution in terms of saturation levels, which is what's called the supersaturated solution, which is what we call the supersaturated solution. So this is a solution that's forced to take on more solute than it normally would. It's forced to dissolve more solute than it normally could at a given temperature. So we say solute content is beyond the maximum. How on earth can you dissolve more solute than the temperature of the solvent allows? Well, that ties into the question I asked just a bit ago. So if I had sugar at 60 degrees Celsius, I could dissolve about 280 grams of sugar into it. If I had, did I say sugar at 60? Water. If I had water at 60 degrees Celsius, I could dissolve about 280 grams of sugar into it. Okay, so sugar dissolves perfectly fine at 60 degrees, so I'm going to write this down. You can't see it yet, but I'll switch back to the camera real soon. 280 grams of sugar dissolved in 100 grams of 60-degree water. Then what we're going to do is cool the water down. There's going to be a cooling process, and you want to do this gradually. You don't want to, dunk an ice cube in there. That's not going to work. But if you let it just cool down at a leisurely pace, then let's say we cool it down to 20 degrees Celsius. That's a little below room temperature, but we'll do it. You'll end up with 280 grams. You know what? Fine. Just here. You can watch me as I'm writing it. We end up with 280 grams of sugar in 100 grams of 20-degree water. And again, it's perfectly dissolved. It doesn't immediately solidify. So going back to the chart, at 20 degrees, it looks like we have a solubility of almost 200 grams. I'm going to say it's 200. So here we've got solubility is 200 grams of sugar. So some of you might be thinking, well, there's 280 grams of sugar and it's in 20-degree water. The water can only take 200 grams, therefore 80 grams of sugar will just undissolve instantly, right? Well, not quite. Not quite. Because it was already dissolved and evenly scattered between the water molecules at a higher temperature, the sugar molecules stay separated. In order for them to solidify, they'd have to, come back in contact with each other, but they can't because they're already surrounded by water molecules. Remember the diagram I had up for ion-dipole interactions. I know sugar's not ionic, but same thing. Because of polarity and because of hydrogen bonding in sugar, water molecules will surround the sugar molecules and isolate them from other sugar molecules in pretty much the same way as you see for those few ions at the top of that diagram. So yeah, the sugar molecules are already blocked off of each other because of the water surrounding them. So in order to get 80 grams of sugar to, I guess, precipitate out, what you'd need to do is kind of disturb that, shake off the, and I see I misspelled supersaturated there, that should be an R. What you need to do is kind of shake off some of the water molecules surrounding some of those sugar molecules so that they can come in contact with each other and actually bond to each other and precipitate out. And if you do that, if you manage to bring the sugar molecules back together, at least 80 grams worth, then you start a process. I guess I mistakenly called it precipitation earlier, but really what it's called is crystallization. So if I either disturb and agitate, so either agitate or seed the solution, agitate or seed the solution. I'll talk about what seeding is in a minute. Can you see all that? Yes. If you agitate or seed the solution, then what we get in the end is, I'll do it in orange, 200 grams of sugar in 100 grams of water, plus 80 grams of sugar crystallized. Can I fit that in here? Let's just write it down here. Crystallized. I think it's with a double L, but don't trust my spelling. 80 grams of sugar crystallize out of the solution back into the solid phase. Okay, so yeah, so this solution that we have before crystallization is what we call a supersaturated solution. It's water whose temperature allows it to dissolve 200 grams, yet there's over 200 grams of sugar that's dissolved in it. It's not very stable, which is why sometimes just shaking it will get crystallization to start. You can imagine physically shaking the solution kind of makes the sugar molecules, despite being surrounded by water, makes them bump into other sugar molecules surrounded by water so hard that they shake off those surrounding water molecules and can actually connect to each other. At least that's one possible theory as to what's going on. But the other thing you can do to a supersaturated solution to crystallize out the excess solute is seeding. So basically what you do there is you, I guess it would work even if it wasn't necessarily solid sugar, but if you put, say, 1 grain of solid sugar into a saturated sugar solution, then that 1 grain of sugar acts as a sort of seed that the crystal can grow from. There's a solid piece of sugar that the other sugar molecules can come into contact with despite being surrounded with water. Maybe I should try and illustrate this. I'm not going to draw the sugar molecule because it's big and complicated and we'd be here all day, but I'll just say this is a representation of a sugar molecule. and it'll be surrounded by water. I'm not going to draw the lone pairs on oxygen to save time. So let's say it's surrounded by water molecules, like so. And in some places the hydrogen end will be closer, in other places the oxygen end will be closer. But yeah, something like this. And suppose you've got a whole bunch of these, and then you've got just one grain of sugar over here. So they're just a bunch of sugar molecules connected to each other, not separated off by water. That's not how you spell sugar. You know what? I'll just abbreviate it SUG. What did I do here? We'll pretend, you know what? I'm not going to write the word sugar every time. Just know that these green things are sugar. Okay, so here you've got, say, a grain of sugar that has a bunch of solid sugar molecules in it. The water might surround the sugar enough to block it off from other surrounded sugar molecules, but if this thing comes close to here, then it's not completely blocked off. There are some openings, there is some exposure. So if this thing gets close, then it can start connecting, it can start bonding to this seed, as we'll call it, this seed crystal. And yeah, the attraction might be strong enough that this sugar molecule just stays stuck to this seed crystal and just becomes part of the overall crystal. And these water molecules, I guess they just float off and go find some other sugar molecule to bug. But yeah, that's basically what's going on when you put in a seed crystal, just a solid sample for the excess dissolved sugar molecules to kind of latch onto. And again, it doesn't actually have to be the same substance as whatever's dissolved in your supersaturated solution. But I mean, if you want a pure crystal, you really should use the same substance, so I don't know what you're thinking using something else. But that's the crystallization process. And the crystallization process is typically going to be an exothermic process. Crystallization is usually an exothermic process. So if you take aqueous sugar and you turn it into solid sugar, that's going to be typically an exothermic process. Delta H less than 0. Delta H is negative. And an easy way to make sense of that, to remember it intuitively, is that taking a solid and breaking it up into separate particles should require energy. I think that's more intuitive for people to remember. Going from solid to kind of liquid is similar to melting things, and melting things usually requires heat. So if going in the reverse direction requires heat, you can conclude that going from aqueous to solid is probably going to release heat. There might be exceptions, but that's what you can typically expect. And yeah, so if sugar crystallizes in water, the water will warm up. If sugar crystallizes in water, then the water will warm up. And that's actually how hand warmers work. I told you we'd get to it. So that right there is a hand warmer. It's one of those gel hand warmers, which is pretty impressive that you can actually reuse them. But yeah, how do they work? So first you have the gel, of course it's not sugar in there, they use, it looks like they said sodium acetate. So they've got sodium acetate in a supersaturated gel, and you click the metal thingy on the hand warmer, and what happens when you click it is you kind of scrape off a tiny unnoticeable amount of solid particles, solid metal particles, that serve as a sort of seed for the sodium acetate to crystallize onto, to latch onto and form an ever-growing crystal. And you can see in that middle picture the crystal is just kind of starting to form. You see a cloudy spot near the right end of that middle picture. And then, of course, as time passes, the crystal just kind of grows until it occupies almost the whole entire packet. But yeah, that is going to release energy into the gel, which will then result in an increase in the gel's temperature, and of course will result in warmer hands during the winter. I could use a hand warmer right now. Now, the other thing about these gel hand warmers is that they're typically reusable. And how do you reuse them? Well, you re-prepare a supersaturated solution by heating up the gel to a temperature where it can dissolve all of that sodium acetate. And then, of course, you let it gradually cool down. It becomes a supersaturated solution again. You click the metal thing, and the whole process starts all over again. Okay, so that's the crystallization process and solubility of solids. Looks like I'm coming down with a case of the sniffles again. That'll probably get annoying. But you know what? I delayed this video because of the sniffles last week, so the show must go on. I think I kind of went all over the place here. I probably cut off some of my sentences earlier too. I can't wait to review this video and see how awkwardly worded some of my statements were. Where was I going with this? Okay, so we've talked about unsaturated, saturated, and supersaturated. Let's see. And that was quantitative solubility for solids. Okay, yeah, and then we're going back to gases now. So, solubility of solids, for the most part, not for all solids, but for most solids, the solubility goes up as you increase the temperature. That is not the case for gases. That is not the case for gases. For gases, the solubility is higher if the temperature is lower. The solubility is higher if the temperature is lower. How does that make sense? Well, you might remember some things from kinetic molecular theory back in, let's see, I think that would have been video number 6 was when we covered gas laws. You might remember some things from kinetic molecular theory, such as the fact that high temperature means high average kinetic energy, high temperature for gases, and I guess also for liquids and solids, but for gases especially, high temperature leads to high average kinetic energy, and kinetic energy is the energy of motion, so that also leads to a high average speed. It's not a direct proportionality, mind you. Kinetic energy is related to the square of the speed. High average speed. So, yeah, if you have some gas particles dissolved in a solution, then can I draw for this? Oh, well, I mean, it's not going to be all that different from what we've drawn before. So let me see. You know what? I won't draw the solvent particles, or should I? You know what? I will. I'll draw a few of them. So let's say the green particles represent the solvent, so water. In this case, let's say each of these circles represents water. And let's say here in orange, let's say I've got some gas particles. So if the gas particles don't have enough energy, if they don't have enough speed, then when they try to go up near the surface, they will typically bump into some water molecules. They'll get slowed down, and they might get slowed down so much that they don't make it to the top. Maybe they even get bounced back down after colliding with a water molecule, and they just stay dissolved in that case. However, if the temperature is higher and they have more speed, then maybe, just maybe, they can, zip out of the solution and, go back into the air. So yeah, high temperature. If you increase the energy of these gas particles, then their chances of just jumping out of the solution increase as the temperature goes up. Pretty simple, straightforward idea there. Higher temperature reduces solubility for gases. Okay, then what can increase the solubility of a gas in a liquid? Pressure. Raising the pressure can increase the solubility, and I don't think I have a chart for that, do I? No, it doesn't look like it. Increasing pressure. And specifically, I'm talking about external pressure. Increasing external pressure can increase solubility for a gas. Oh my God, this new marker has a really strong smell. Maybe the fact that you can't smell things through the internet yet is a good thing. Yeah, increasing the external pressure on a solution can increase the solubility of gas in that solution. What did I do here? Oh, okay. Yep, I just made it invisible. I thought something went wrong with the camera. False alarm. So yeah, increasing the external pressure can increase the solubility of a gas. How does that work? Well, if you increase the pressure, then you can think of it as there's more air above the surface of the solution. Actually, you don't need to add more air, but let's represent increased pressure with lots of air particles here. So at a high pressure, the collisions between these air particles above the surface of the solution are going to be pretty frequent. The collisions are going to happen pretty frequently and pretty strongly, and so if one of these orange gas particles does manage to escape out of the solution, maybe because it has to navigate through all these gas particles now, maybe, just maybe, it'll, bump into one of these and bounce back down into the solution again. The likelihood of collision is very high, and chances are that if the external pressure is higher than Should I bring it up now? Sure, why not? The vapor pressure of the solution then, well, no, I guess vapor pressure wouldn't be the best term to use here. Yeah, you know what? We'll talk about vapor pressure later. It's coming up. Don't you worry. It's coming up. But let me see. I lost my train of thought. What was I going to say? Yeah, if the external pressure on the outside is higher, you can imagine basically the air just pressing down on the solution and pushing down any gas particles that try to escape, or most of them, because some will manage to get out, of course. But the point is to limit how many actually do get out, if you actually want to keep these gas particles dissolved in the water, or whatever solvent you have. But yeah, so an increase in pressure, the more you squeeze the gas, the more you apply pressure to it, the more you can keep it stuffed in the solvent. And there is actually a relationship. We pretend it's linear, even though it's not. There is a relationship between pressure and gas solubility called Henry's law. Which says that the solubility of a gas is equal to some constant, depends on what the gas is, times the pressure times the external pressure. So basically the idea that Henry's law gives us is that if you double the pressure, you double the solubility of the gas. That's not entirely true. It's approximately true for a lot of gases, but it's not all that true. So, you know, Henry's law, I don't feel it's all that realistic. I don't think it's realistic enough to be using, but there you go. It's there in case you need to know it. You probably won't be asked a lot about Henry's law anyway. But, you know, it's one of those obligatory mentions. So yeah, gases can definitely dissolve in liquids. In fact, you've probably noticed gas bubbles in a cup of water before. And also, for that image you see on the right, that's what happens as a result of increasing ocean temperatures. When the temperatures of the oceans go up, the oxygen dissolved in seawater it'll become less soluble. The oxygen will bubble out of the water, and then the fish can't breathe, and then all of a sudden you notice dead fish floating on the surface of the ocean. So there's that. Another example that illustrates the effect of pressure on solubility of gases is, let me see, where did I put it? There it is. Sodas, carbonated beverages. In this case, you have carbon dioxide that's dissolved in whatever your carbonated beverage of choice is. I don't really drink that stuff, but you know, well, maybe I'll drink like one soda every 2 years, approximately, but usually all I drink is water and tea. So many different flavors of tea. But yeah, you dissolve lots and lots of carbon dioxide into these sugary drinks by doing two things, by manipulating both the pressure and temperature factors. So, of course, there's a lot of pressure in the can, and you release it as soon as you open the can or the bottle or whatever the container is. But the other thing that we don't take into account as much is the temperature. These drinks are usually served cold. In fact, best served cold. If you drink warm soda, you'll notice that it tastes flat. Or if you leave it out for long enough for the pressure to go down and for all the gas particles to come out of it, that'll also result in it tasting flat, even if you do manage to keep it cool. So yeah, that example might bring it closer to home. I think we're at a good point now that we can start looking at some problems. Yeah, let me go ahead and pull up some problems and see what we've got here. We won't do all of them, of course. You know the deal by now. I'll pick out the ones that I feel might be worth covering. Number 1, I think we've talked about. Number 2... Oh, that relies on a figure, which I don't have for you. Or maybe I did have it, but it's whatever. Number 3, when potassium nitrate is dissolved in water, the resulting solution is significantly colder than the water was originally. Okay, we've talked about this. So part A is the dissolution of potassium nitrate, an endothermic or exothermic process. If the water is colder, if the solution is colder than the water was originally, then the potassium nitrate took energy out of the water. It took heat out of the water, so that must mean it required heat to dissolve. It's an endothermic process. What conclusions can you draw about the intermolecular attractions involved in the process? That the intermolecular attractions between the water molecules plus the intermolecular attractions between the potassium and nitrate ions before dissolving must have been stronger than the interactions between the potassium ions, the nitrate ions, and the water after dissolving. And part C is the resulting solution an ideal solution. Oh, okay. So we haven't really talked about ideal solutions. Let's talk about that real quick. So ideal solutions, what are they? Not that useful of a concept in my opinion, at least at this level of chemistry. Maybe at a higher level it would be more important, but an ideal solution is a solution in which solvent-solvent interactions solute interactions and solute-solvent interactions I guess I should include the and there. And solute-solvent interactions are equally strong. A very clunky definition, but basically what this means is if I have my potassium nitrate, so just, the solute-solute interactions, in other words, if I've got potassium with nitrate, let me see, so nitrate, NO3 minus, why am I doing this? I think I remember one of these being double bonded, but I'm not going to worry about getting the correct Lewis structure. It's not worth our time. But yeah, the interaction between potassium and nitrate ions versus the interaction between, let's say, well, not let's say, it is water in our example, the interactions between water molecules and other water molecules. And the interactions between water molecules and potassium or nitrate ions. So I'll just draw, yeah, let's do one there and another there. And I'll just do the potassium ions. I'm not going to do it again for the nitrate ions. But yeah, let's put a potassium ion in there, and we've got some interaction between the water and potassium. Something similar happens between water and nitrate, but I'm not going to waste time drawing that. So basically what they're saying is that all these interactions are equally strong, and if that were the case, if we really did have an ideal solution where all these interactions were of equal strength, then breaking these interactions and breaking these interactions and replacing them with these interactions that have the same strength would result in no overall change in the total energy. The delta H would be zero. It would be neither exothermic nor endothermic. And clearly we have concluded that the dissolution of potassium nitrate is an endothermic process. We said that in part A. So the resulting solution is not an ideal solution. Ideal solutions are kind of hard to come by, which is why I think the ideal solution concept isn't all that useful at this level of chemistry, but, you know, it's another thing that you just kind of need to know about. You need to know about it more than you actually need to know it. So yeah, that finishes up Part C of Problem 3. Problem 4, give an example of each of the following types of solutions. We had that chart that I put up towards the beginning of this video, so you can go back to that if you need to see examples, or you can do some Googling and look for other examples. Number 5, indicate the most important types of intermolecular attractions in each of the following solutions. The solution in figure 2, which I don't think I have, so we'll skip it. B, we've got nitrogen monoxide liquid in carbon monoxide liquid. What intermolecular attraction is responsible for the dissolution process there? Well, you might notice that nitrogen and oxygen have some different electronegativities. They're close, but I suppose they're different enough to be somewhat polar. Carbon monoxide, also pretty polar. So I would say dipole-dipole interactions for those. Chlorine and bromine. No difference in electronegativity for either of those, so no polarity, which only leaves London dispersion forces. So the ability of chlorine to dissolve in bromine must be due to the London dispersion forces between them. Part D, HCl gas, hydrochloric acid gas in benzene. I wouldn't think that hydrochloric acid would dissolve all that well in benzene, because if you look at their structures, I guess I haven't, yeah, let's just go with light green. So if we look at their structures, HCl is going to be a polar molecule with the negative end being chlorine. And benzene, on the other hand, I don't think I've ever shown you guys benzene. Have I? I don't think I have. Benzene is a hexagon-shaped ring, a hexagonal ring of carbons. Okay, that's not a very good hexagon, but yeah, with hydrogens attached to each of the carbons like so. Can you see that on the screen? Yeah. Okay, I probably should have drawn it higher up on the page. And then you've got double bonds here, here, and here. You could also have them, you could also have the double bonds here, here, and here instead. That's right, benzene has resonance structures. And if you don't remember what resonance structures are, go back to, I think it was video number 9. Whichever video we did that had all the Lewis structures in it. I think it was the end of video number 8 and the beginning of video number 9, if my memory is correct. But yeah, benzene has resonance structures. We're not going to talk about that. That's a different topic we've covered before. But yeah, look at all the symmetry that you've got going on here. Plus, there's no difference in electronegativity between carbon and other carbon. Carbon and hydrogen has very small difference in electronegativity, so those bonds aren't very polar, but even if they were polar, because of the symmetry, all of those dipole moments cancel out. So we've got a polar versus a nonpolar. I guess they can still dissolve because even the polar substance is going to have some London dispersion forces, but that's it. Polarity isn't there to help. I guess the London dispersion forces alone might be strong enough to dissolve some HCl and benzene, but I would imagine it won't be a whole lot, because remember, like dissolves like. Or maybe they should modify the statement to say, like best dissolves like. But now I'm rambling. So yeah, it's got to be the London dispersion forces between the HCl and the C6H6. Otherwise, there's just no other type of interaction that can form between them. Part E, methanol, CH3OH. I think I drew that earlier. In water. Well, we already explained that one. It's because of hydrogen bonding. So, methanol should be quite soluble in water, and vice versa, or, to use the proper term, miscible. But yeah, that's number 5. Let's take a look at another one. What else do I have here? On this page, let's see. Number 6, predict whether each of the following substances would be more soluble in water or in a hydrocarbon such as heptane, which is a nonpolar solvent. Vegetable oil. So this is just the like dissolves like rule again. Vegetable oil is probably going to dissolve better in heptane rather than water. If you put vegetable oil in water, you can do this at home, then you'll see that the oil just kind of floats on top of the water and doesn't really dissolve. Probably a negligible amount does dissolve, but most of it just floats on the top and stays completely separate. And if you pour salt on top of it, you get an effect that's kind of like a lava lamp. So you might want to try that. Put a little bit of oil in some water, let the oil creep up to the top, and then pour some salt on top of it. Just sprinkle some salt, and the salt will drag down the oil will get down to the bottom, and then it'll float back up to the top, and it kind of looks like a lava lamp, except without all the pretty colors. Maybe you could use food coloring to deal with that. But anyway, next up is isopropyl alcohol, which is polar. That's probably going to dissolve better in water than in heptane. And potassium bromide is ionic, which will probably dissolve better in water because water can form ion-dipole interactions with ionic compounds. Okay, number 7, heat is released when some solutions form, and heat is absorbed when other solutions form. Provide a molecular explanation. We already did. And I guess we didn't give a complete explanation for the spontaneity of dissolution when the solution gets colder, but that's because we haven't talked about spontaneity, so I don't expect you to know what spontaneous means right now. We will cover that in video number 16 on thermodynamics, so that's coming later. Number 8, solutions of hydrogen and palladium may be formed by exposing palladium metal to hydrogen gas. The concentration of hydrogen in the palladium depends on the pressure of hydrogen gas applied, but in a more complex fashion than can be described by Henry's law. Yeah, this was what I was talking about earlier. Henry's law says that the relationship between gas solubility and pressure is approximately linear, but not really. Not really. It's very easy to find exceptions to Henry's law. Anyway, under certain conditions, 0.94 grams of hydrogen gas is dissolved in 215 grams of palladium metal, and the solution density is 10.8 grams per cubic centimeter. Determine the molarity of this solution, the molality, and the percent by mass. We haven't talked about that yet. Let me see. Should I go over this now, or should we skip it and go back to it? Well, let me see what the other questions are about. Maybe we should cover this now, because I really do want to do something like number 8, but I don't think now is the right time for it. Let me see. I guess I'll just circle number 8 on my notes so that I remember to go back to it. And let's just go to something else. Okay, let's see what we have here. Number 9, explain why the sodium and chloride ions are strongly solvated in water but not in hexane. We already talked about that. Number 10, explain why solutions of HBr in benzene, hydrobromic acid in benzene, are non-conductive while solutions in water are conductive. Ooh, okay. This one might be interesting. So, hydrobromic acid in benzene versus hydrobromic acid in water. So this ties back into the HCl in benzene question that I was talking about just a few minutes ago. Okay, so yeah, when HCl dissolves in benzene, it's not going to ionize. There's no reason for it to ionize because there's no polarity here. The benzene wouldn't be attracted to ions anyway. Okay. So I guess this is kind of tying back into that. Okay, so yeah. If HBr dissolves in benzene, and by the way, benzene, instead of drawing it like this every single time, chemists abbreviate it by just drawing a hexagon with a circle in the middle. The circle in the middle is supposed to represent the fact that the pi electrons are kind of shared across all of the carbon bonds. Because we've got two different resonance structures, and if you blend them together, That's basically what the circle is representing. You can also draw benzene as this or as this. But yeah, the thing with the circle in between is basically implying that the real molecule is a blend between this and this. Anyway, HBr in benzene, so hydrobromic acid in benzene, and I guess I should draw the lone pairs there. It's not going to ionize. It's not going to ionize. First of all, it's probably not going to dissolve that well in benzene to begin with. At least that's my prediction. So, of course it's not going to conduct electricity, because if it doesn't split up into ions all that well, then you don't have a lot of moving charge in that solution, if any. And charge needs to move in order to conduct electricity. For electricity to move through the circuit, charge has to move. Whereas HBr in water is going to work just fine, because in water you'll separate the hydrobromic acid into hydrogen ions and bromide ions. The hydrogen ions, of course, get surrounded by water molecules with the oxygen facing the positive charge, whereas the bromide ions will be surrounded with water molecules where the hydrogen faces the negative charge of the bromide. All right. And I guess I should circle this and this, yeah, to keep them as their own things. But yeah, there you go. So you do get the cations and anions to split up, and they can move around, surrounded by water molecules, yes, but still free to move around in the solution. So there you go. I'm guessing my choice of color there is not good for colorblind people. Maybe I should retrace this in green. Better contrast. I mean, I don't even know if this helps if you're colorblind, but I had a colorblind student once, so I'm a little bit more mindful of that than most people, but I'm not that mindful. I'm sure you can go back through my older videos and find plenty of examples that aren't very colorblind supportive, but I try when I remember. Let's see, so that was number 10. Number 11, is it worth our while? Consider the solutions presented. Which of the following sketches best represents the ions in a solution of iron 3 nitrate? Yeah, that looks like iron 3 nitrate. Solution A, solution B, or solution C? Well, not A, B, and C. They're X, Y, and Z. I think this one is pretty obvious, but it would be solution Z. Iron nitrate dissolves pretty much completely, so the iron should be separate from the nitrate ions. They shouldn't be stuck together. X shows them just completely undissolved, which doesn't make sense. They even said that the iron nitrate, or the iron 3 nitrate, is aqueous. So we already know it's fully dissolved. Y just shows the iron dissolving and not the nitrate, which also doesn't make sense. Where did that extra iron come from? Actually, wait. No, it doesn't. Looking at it more closely, it shows the iron separated off, and then the 3 nitrates are somehow just bonded to each other and clustered together in sets of 3. And that doesn't make sense because nitrate ions are negatively charged. They should repel each other. So yeah, I think this one was pretty obviously Z. Part B, write a balanced chemical equation showing the products of the dissolution. I mean, I think that's easy enough to do, but we'll do it real quick. Why not? So you've got, I guess I'll do it in orange. Yeah, let's do it here. There should be enough space for it. Iron 3 nitrate, FeNO3, 3. Just splits up, so it starts out as a solid and splits up into the iron 3 ion, which has a positive 3 charge in the aqueous state, plus 3 times the nitrate ion, which will also be in the aqueous state. Pretty simple, straightforward, no need to overthink it, and yes, it's balanced. Okay. I would hope that balancing equations is kind of a mindless task for you at this point in the course. If it's not, you may want to practice. Is number 12 worth our while? Compare the processes that occur when methanol, hydrogen chloride, or hydrochloric acid in other words, and sodium hydroxide dissolve in water. Compare them and then write equations and prepare sketches showing the form in which each of these compounds is present in its respective solution. I mean, we kind of illustrated that already. So methanol exhibits hydrogen bonding. Hydrogen chloride, I guess in this case, they're treating it as being more molecular than ionic, which they can do. Again, HCl is one of those that can be seen as molecular in some cases and ionic in others. But yeah, in this case, they just want it to represent a polar molecule. And sodium hydroxide, they just want that to represent an ionic compound, a highly soluble ionic compound. And we've already seen examples of all of those. I mean, if you go back to it, where did we put it? Not there. Wait, is that it? No. I think it was the first page that we did. Yeah. So I showed you a diagram for ionic compounds in water. There's a hydrogen bonding compound in water. And there's just a plain old polar compound dissolving in water. That's basically what they want you to do. Just draw the water molecules and how they surround the different substances. Okay, we don't need to spend time on that. Number 13, what is the expected electrical conductivity of the following solutions? Sodium hydroxide solution. So many hydroxides are not that soluble, if you remember your solubility rules from video number 4. But when paired with sodium or ammonium or any of the group 1 metals, lithium, sodium, potassium, rubidium, cesium, francium, then you get very high solubility. Sodium hydroxide is very soluble, separates into ions pretty much completely. It's a strong electrolyte, so it's going to conduct electricity really well. Hydrochloric acid, same thing. It's going to conduct electricity really, really well. Hydrochloric acid is one of the strong acids. We'll talk about that when we get to acids and bases, which is, I think, video number 14 is what I have it planned for. But yeah, HCl is going to completely or almost completely separate into ions, so strong electrolyte again. C6H12O6. Okay, that's glucose or sugar. It doesn't split up into ions when it dissolves in water. It dissolves in water due to all of the hydrogen bonding sites. You can go to Wikipedia, I think, and look up the structure for glucose. It's a pretty big molecule, but there's lots of H's and OH's all over that thing, so lots of hydrogen bonding. But it's not going to split up into ions. That's a non-electrolyte solution. It's not going to conduct electricity at all. Aqueous NH3. This one might be a little harder to tell if you don't have much experience in chemistry. So ammonia, when ammonia is dissolved in water, it actually reacts with the water. So when ammonia interacts with water, it actually reacts with the water and forms NH4+. It takes a hydrogen off of the water, and so the water turns into hydroxide. Okay, and I guess the water would be in the liquid state. Ammonia is typically a gas. So yeah, when you put ammonia in water, it will ionize and produce the ammonium ion and the hydroxide ion, but not completely. It's not going to completely ionize. There's a limited amount of ammonium that you actually form. Some of it will still stay as NH3 dissolved in water, so maybe what I should do is, in parentheses, plus some intact NH3 as you know, a dissolved molecule. So it would be in the aqueous phase. So this is an example of a weak electrolyte. I guess you could expect that because, I mean, we already had 2 examples of strong electrolytes and 1 of a non-electrolyte, so by process of elimination, you'd expect NH3 to be a weak electrolyte, but there's the explanation for why it's a weak electrolyte. So yeah, some of the NH3 forms ions, but not all of it. Weak electrolyte. Okay, let's see what else we've got. 14 and 15. 14, why are most solid ionic compounds electrically non-conductive, whereas aqueous solutions of ionic compounds are good conductors? Well, the reason for that is simple. When they're solid, they're locked in place. The ions can't move, and charge has to move in order to conduct electricity. When you separate them from each other in water, then they're free to move around. And then the other part of the question, would you expect a liquid ionic compound, that is after you melt it, to be electrically conductive or non-conductive? Explain. A molten ionic compound is definitely going to be conductive because when it's in the liquid form, the positive ions and negative ions can slide around past each other. We talked about that in the previous video, in fact. Not about ionic compounds specifically, I don't think, but we did talk about the structure of liquids compared to solids. The particles of a liquid can move around past each other. There is some freedom of movement there. So yeah, molten ionic compounds can definitely conduct electricity. In fact, melting might be the only way to conduct electricity with some ionic compounds, such as calcium carbonate, because as we said earlier, it doesn't dissolve all that well in water. If you melt it, however, you can use it to conduct electricity. Okay, number 15. Indicate the most important type of intermolecular attraction responsible for solvation in each of the following solutions. We already did something like this, so I'll pass, but you can practice with that on your own if you like. What else do we have? If you're wondering why I keep on switching back to the camera when going to the next set of problems, it's because the software I'm using kind of automatically picks or automatically goes back to the last set of slides that I was looking at, and it's hard to explain, but it's easier for me this way. Is all I'm going to say about it. So if that feels random to you, maybe I should have explained that a long time ago. By now you're probably used to it. Anyway, 16, is that worth our time? Suppose you are presented with a clear solution of sodium thiosulfate. How could you determine whether the solution is unsaturated, saturated, or supersaturated? The test in all three cases is really, really simple. You just add more sodium thiosulfate. It's the same test regardless of which state it's in. If you add some sodium thiosulfate, then one of three things will happen. Of course, if you add too much, then you might ruin your experiment and draw the wrong conclusion, but if I add some sodium thiosulfate, add some, not too much, just a little bit, add some sodium thiosulfate, Na2S2O3, and then one of three things will happen. Either it dissolves. Of course, you're going to need to stir. I don't think I talked about the effect of stirring all that much, did I? I'll need to go back and talk about some of the factors that affect how quickly things dissolve. So I'll make sure to do that after I wrap this up. So either it dissolves or it doesn't dissolve. Or crystals start forming. Crystals begin to form. Those are the three different things that can happen. If you can add some sodium thiosulfate and you're still able to dissolve it, that means the solution that you were given was not maxed out yet. It was unsaturated. If you try to put in more sodium thiosulfate and it won't dissolve, then that means that you've already dissolved the maximum amount. You've already maxed out your solution, and the solution is saturated. But if crystals begin to form, then not only is your solution saturated, but it was supersaturated. And it was in an unstable state, and you basically prodded it into crystallizing out the excess solute. So this would happen if it were supersaturated. You would see crystallization after adding some more of the solute. So yeah, really, really simple test. And I think that takes care of that question. Now, before I forget, let me talk about something that I forgot to mention earlier, factors that affect the rate of solvation or dissolution. Rate of solvation or dissolution is affected by three things, at least three things that I can think of off the top of my head. Temperature. Temperature doesn't just increase the solubility, but it also increases the rate at which things can dissolve, how quickly things dissolve. If you pour some, well, I shouldn't say pour, but if you sprinkle some salt in hot water and you sprinkle the same amount of salt in the same amount of cold water and you compare the two, then you'll notice that it dissolves faster in the hot water. I believe the opposite would be true for gases, but for most gases you can't really see because most gases are colorless, at least most of the ones we interact with on a daily basis. So I'm not so sure about gases, but I would assume it's the opposite. The other thing that affects the rate of solvation is agitation or stirring. The harder you stir it, the faster it dissolves. And what was the other factor? Surface area. Or I should say the exposed surface area. Just like when we were talking about London dispersion forces in the last video and the factors that affect polarizability, we talked about exposed surface area. Same thing for the dissolution process. The more exposed surface area there is to your solute, the quicker it will dissolve. So why do these three factors affect the rate of solvation? Temperature increases the average kinetic energy of the particles. So at higher temperatures, you have, let's say our solvent is water. The water molecules move around faster, so they come into contact with your solute particles sooner and can start, surrounding them and isolating them from their fellow solute particles. Agitation kind of does the same thing. If you shake the solution or stir it, you're basically giving the solvent particles some energy and you're making them move faster, come into contact with the solute particles sooner. And I guess you might also be kind of disturbing the bonds between the solute particles, so that's an added bonus. And then the surface area factor, the more surface area, the more exposed the solute particles are to the solvent. So the sooner the solvent molecules can come into contact with the solute particles. So yeah, that's basically it. So for surface area, think of three different forms of sugar. You've got regular cane sugar, you've got sugar cubes, and then you've got the, what do they call it? The powdered sugar, which you can actually make by just taking regular cane sugar and just grinding it, or pounding it with a hammer or whatever until it's a fine powder. But yeah, the fine powder is going to have the most exposed surface area because when it's a fine powder, you can really get in between the sugar molecules a lot more easily than you could with grain sugar, and way, way easier than with sugar cubes. With sugar cubes, you can only interact with the sugar that's on the outside of the cube. The sugar on the inside is kind of blocked off and protected. But yeah, so those are three things that affect the rate at which things dissolve. Not the most crucial of details, but it's good to remember that conceptually. And who knows, maybe it'll be useful in the kitchen. Number 17. Supersaturated solutions of most solids in water are prepared by cooling saturated solutions. Supersaturated solutions of most gases in water are prepared by heating saturated solutions. Explain the reason for the difference, or the reasons for the difference in the two procedures. Because of the way their solubilities work. Remember what we said with our first supersaturated example. we started with a temperature where the solubility was higher, and then we went to a temperature where the solubility was lower, and the way to do that was by cooling, because for solids the lower solubility is at the colder temperature, but for gases it's the opposite. For gases, the lower solubility is usually at the higher temperature. So you start with a colder temperature so you can dissolve more gas, and then you raise the temperature. And I guess you do it in a sealed container or something like that so that the gas particles can't escape. I'm not entirely sure. But that's how you would supersaturate a solution involving a gas. So that was a pretty quick one. Do we want to do some problems from here? Let's see. 18. Suggest an explanation for the observations that ethanol is completely miscible with water and that ethane thiol is soluble only to the extent of 1.5 grams per 100 milliliters of water. Okay. So I guess it's just a difference in the strength of the interaction. Ethanol has hydrogen bonding, and so does water, so they can connect with each other really well. So well, in fact, that there is no maximum solubility. You can dissolve as much water as you want in methanol, or wait, did I say methanol? Ethanol. And you can dissolve as much ethanol as you want in water. It's not solubility, it's miscibility. The liquids just mix no matter what the ratio. Whereas with ethane thiol, which is pretty much the same thing, except replace the oxygen in ethanol with sulfur, well, sulfur has a lower electronegativity. You don't really get hydrogen bonding there. It's just polar. And dipole-dipole interactions are weaker than hydrogen bonding interactions, so it's not going to be as attracted to the water as ethanol was, and so it's not going to be as soluble. Pretty simple explanation there. Do we want to do 19? Calculate the percent by mass of potassium bromide in a saturated... Yeah, we can skip that. We've done percent by mass before, and we will do it later in this video, but for now I think we'll pass on it. Number 20. Which of the following gases is expected to be most soluble in water? Explain your reasoning. Okay, so that's another factor affecting the solubility of gases that I didn't mention, which is polarity. So we talked about the temperature and pressure effects, but polarity also makes a difference. The higher the polarity, the greater the solubility in other polar solvents. So CH4, methane, not going to be very soluble in water. It doesn't have a lot of polarity to it. Carbon tetrachloride, same thing, not very soluble in water. It's not all that polar. CHCl3, on the other hand, that one is going to be polar. The dipole moments don't exactly cancel out. And I think CHCl3 may have been one of the examples I showed in the previous video. So if you're not convinced that it's polar, you might want to go back to that video, because I'm pretty sure I covered it. Or I covered something similar to it. But yeah, that's 20. 21. At 0 Celsius and 1 atmosphere, as much as 0.7 grams of oxygen can dissolve in 1 liter of water. At 0 degrees and 4 atmospheres, how many grams of oxygen dissolve in 1 liter of water? Okay, so this is Henry's law. Basically, if you have 4 times the pressure, so The only thing that changed is they went from a pressure of 1 atmosphere to 4. At 4 times the pressure, you can dissolve approximately 4 times as much gas, according to Henry's law. But really it depends on the gas, and it's not all that true, so, you know, since you have no other information, Henry's law is the way to go. But if you were doing this in a professional laboratory setting, you'd probably have to consider more things, and you'd be given the tools to take those things into consideration. But yeah, 4 times 0.7 would be 2.8, so 2.8 grams of oxygen is what I predict you can dissolve in a liter of water at 4 atmospheres and 0 Celsius. Do we want to do 22? It says refer to a figure that I probably don't have. How did the concentration of dissolved CO2 in the beverage change when the bottle was opened? Oh, I don't even need to see the figure to answer that question. If you open the bottle, then you change the external pressure from whatever the pressure was inside the bottle when it was closed to the atmospheric pressure, which is in all likelihood going to be considerably lower. So yeah, you lower the pressure, you decrease the solubility, so carbon dioxide will start to bubble out, because you can't keep it dissolved if the pressure isn't kept high. What caused the change? I guess I kind of explained it already. Is the beverage unsaturated, saturated, or supersaturated with CO2? That's a good question. I would guess supersaturated? Yeah, I would guess supersaturated, because they've forcibly pressurized the contents of the can, or whatever the container is for this beverage. I'd imagine it's just a regular aluminum can. So yeah, I would say supersaturated, because as soon as you release the pressure, a ton of carbon dioxide comes out. So maybe there was more carbon dioxide in there than the liquid could normally hold. But, you know, that's just kind of speculation at this point. You can do some Googling around if you're really concerned about the inner workings of soda. I think if you care about Diet Coke specifically, MatPat might be the person to ask. And if you don't know who MatPat is, look up the Game Theorists channel on YouTube. 23. The Henry's law constant for carbon dioxide is 3.4 times 10 to the negative 2 molar per atmosphere at 25 degrees Celsius, assuming ideal solution behavior. Oh yeah, by the way, Henry's law assumes that you're working with ideal solutions, which is practically no solution anywhere on Earth. But anyway, assuming ideal solution behavior, what pressure of carbon dioxide is needed to maintain a CO2 concentration of 0.1 molar in a can of lemon lime soda? Okay, so this is simple, straightforward. You just use the Henry's law equation. It's not all that bad. Let's just do it real quick. So what did they give us? They gave us the Henry's law constant K equals, they said 3.4 times 10 to the negative 2. I'm just going to write that as 0.034 molar per atmosphere. Henry's law says that the solubility is equal to K times P. So let's see here. What pressure of carbon dioxide is needed to maintain a concentration of 0.1 molar? Okay, so I guess the solubility in this case is just given in units of concentration, which is fine. That can work. So solubility can be given in moles per liter, grams per liter, grams per 100 milliliter, grams per 100 gram. There are all sorts of units for solubility, and they also tend to work as units of concentration as well. So no surprise there. No need to be bothered by that. And yeah, they're just asking at what pressure does the carbon dioxide need to be. So just plug in the numbers that we have. We've got 0.10 molar equals 0.034 molar per atmosphere times the pressure, which of course is going to have to come out in atmospheres in order for these units to work out. So yeah, 0.10 divided by 0.034 is about 2.9. So we get a pressure of about 2.9 atmospheres is what you'd need to have in order to dissolve that much carbon dioxide. Okay, that wasn't too bad. That's probably the only Henry's Law question you'll ever be asked. If they ask about it at all, you'll be asked just one simple, straightforward question like that, and that'll be the end of it. Unless your teacher is feeling particularly sadistic. Or, if you're taking some course that really, really cares about this stuff. For me, at least, as long as you conceptually understand how the solubility of gases relates to pressure, that's good enough for me. 24 is another Henry's Law equation problem. We'll skip it. 25, assuming ideal solution behavior, how many liters of HCl gas measured at 30 degrees Celsius and 745 torrs are required to prepare 1.25 liters of a 3.20 molar solution of hydrochloric acid? So, okay. So this is not a Henry's Law problem. And if you think it is, it can be very easy to overthink it. But yeah, this is not a Henry's Law problem. So with this, what they want you to do is use the ideal gas equation. Do I really want to do this? Okay, sure, why not? I'll set it up. I'll set it up at the very least. So they want the liters of gas. So they want the volume of the gas. And I'm going to call it V gas because they're also giving us the volume of the solution, and I want to be able to tell those apart. So they want us to find out what volume of gas we need, and they gave us the temperature is 30 degrees Celsius, which, if you add 273 to that, would be 303 kelvins. And they gave us the pressure is 745 torrs, which you can convert to atmospheres if you want, or you can use the ideal gas constant that works with liters and torrs, which I think was 62.36 if memory serves, but you can look it up. And we've got 1.25 liters, so this is V of solution, is 1.25 liters, and the molarity of the solution is 3.20 molar. molarity is 3.20 molar, or maybe I should write it as moles per liter, because some people will see a capital M here and a capital M there, and then they'll cancel them out and come up with this weird idea that 1 is equal to 3.20. Yeah, I'll just keep it in moles per liter. And yeah, so here's what you need to do. I won't do it for you, but I'll at least map it out. Volume of solution in liters times the moles per liter will give you the moles of HCl gas, so you'll be able to get N of HCl gas. And once you have N, so N is equal to M times V solution. Once you've got that, you have pretty much everything you need to calculate the gas volume, because ideal gas equation, pressure times the volume of the gas is equal to the moles of HCl gas times the ideal gas constant, pick the appropriate one for the units that you're working with, times the Kelvin temperature. And yeah, divide by P, and there you go. So that's the setup for that problem. It can be very easy to overthink it because, you know, you just got it after a Henry's law problem, so it's easy to think that they forgot to give you a Henry's law constant or something like that, but it's just simple gas laws. Let's see, do we have more problems we want to look at before covering units of concentration and colligative properties? Let's see, 26. Wait, where did my note card go? There it is. Is 26 worth our time? Which is or are part of the macroscopic domain of solutions, and which is or are part of the microscopic domain? I love the way they word that to make it as confusing and convoluted as possible. Wow. Boiling point elevation, we haven't talked about that yet. Non-stoichiometric compound. I'm not even sure what they mean by that, but okay. Osmosis, we haven't talked about. Okay, let me look at these other problems real quick. I think we might want to do some more topical coverage before we go back to these problems. Okay, potassium nitrate. Okay, yeah, we're not ready for these yet. For number 26, I will comment on one thing at the very least. So for number 26, when they're talking about macroscopic versus microscopic, basically, which of those properties are properties that are properties of like the solution as a whole versus microscopic properties, which are like, you know, properties of individual particles. So, for example, hydrogen bonding, I would say, is probably more of a microscopic property. It's between two particles, whereas something like pressure or temperature is a macroscopic property. That's a property of the solution as a whole. But yeah, I don't like the way that question is phrased, but that's kind of what they're getting at there. Anyway, let's go ahead and talk a little bit more about solutions and maybe review something that you may have heard before, because I'm pretty sure I talked about it previously, maybe in video number 4. Lots of callbacks to video number 4 in this recording. If you don't remember much about solutions, maybe review that video in its entirety. It'll probably help. Anyway, I want to start talking about the measures of concentration. I know I've brought it up before, but there are different measures of concentration that are out there. We've dealt with molarity quite a bit, but there are definitely other measures of concentration, and each measure can be useful for different things. I think I mentioned that the last time I talked about different measures of concentration. But yeah, you've got molarity, which is moles per liter, very useful for stoichiometry. Molarity, so that's moles per liter. Moles of solute per liters of solution. This is going to be important pretty soon. This is useful for stoichiometry. You've got something called molality, which we will look into a little bit more in this chapter. Molality, which is given in moles of solute over kilograms of solvent, not kilograms of solution, kilograms of solvent. Very important difference when you compare and contrast molality and molarity. In molarity, the denominator is a property of the whole solution, whereas with molality, it's just a property of the solvent alone. So this is useful for examining the physical properties of solutions. Molality is useful when examining physical properties. Physical properties tend to depend on the amount of something, and the amount of a substance is indicated by the mass, which is why kilograms of solvent is used instead of liters of solution. We're also going to look at mole fraction. We've done mole fraction before. If you remember, we brought up mole fractions when discussing gases. So I guess I'll talk about this here when talking about gases and pressure, partial pressures especially. That's where mole fractions tend to be useful, so that's going to be moles of solute over moles of solution. That's not how you spell solution. I guess I'll write it down here. Solution. Okay, and the other big one that we're going to look at, which was mentioned in some of the problems we saw actually, is percent mass, or percent composition, which can be defined in different ways, but for us it's going to be mass of solute, whether it's in grams or kilograms or whatever. We're typically going to work in grams, but mass of solute over mass of the whole solution times 100%. And there are other measures of concentration that are useful, like parts per million and parts per billion are useful for the environmental sciences and for setting, environmental safety standards and whatnot. But we're not going to talk about them in this chapter. Just these four are going to be particularly relevant. Percent mass, I guess, is most commonly used in industry and manufacturing because it's really easy to calculate. Manufacturing, can I even fit that in there? Yeah, you can't really read it all that well, but that's supposed to say manufacturing. We typically use percent mass in manufacturing. You probably see it on food labels all the time. 5% distilled white vinegar or whatever. That's usually just a percent mass because it's very easy to calculate. You weigh the solute, and then you dissolve it, and then you weigh the solution. You divide and you multiply by 100%. You don't need to know anything about molar mass or moles or really any chemistry. You don't need to know chemistry to calculate percent mass. And that's why it's used. It's really easy. Yeah, so these different measures of concentration will be given in problems, and sometimes you might be given the wrong measure. You might be given a measure of concentration that's not useful for the problem that you have to do, so you need to convert between one of these and the other three. And so I think now is a good time to practice doing conversions between them before we go any further. Let's go back to, I think it was problem number 8. Hold on, where's my pen? There it is. Let me mark this on my note card so that I don't lose my place. Okay, that's where we're at. And I think, yeah, I marked problem number 8. So let me go back and dig that up. Okay, there it is. Going back to problem number 8. So, hydrogen and palladium. The concentration of hydrogen and palladium depends on the pressure applied. We already read that. Under certain conditions, 0.94 grams of hydrogen gas is dissolved in 215 grams of palladium metal. And they also give us the solution density. And it says to convert from, well, whatever it is we have right now to molarity, molality, and percent mass. And as a bonus, let's also do mole fraction. So we've got 0.94 grams of hydrogen, 215 grams of palladium. Let's go ahead and write that stuff down on a new page. So we've got 0.94 grams of hydrogen, and we've got, they said 215 grams of palladium. And I guess we should look up their molar masses. So hydrogen, of course, is hydrogen gas is 2 times that, so 2.016 grams per mole versus palladium, which is, according to my table, 106.42 grams per mole. Okay, so, and they gave us the density. They gave us a density of 10.8 grams per cubic centimeter. And a cubic centimeter is also known as a milliliter. 10.8 grams per cubic centimeter, which equals 10.8 grams per milliliter. Okay, let's see. So they asked for the molarity first, then the molality, then the percent mass, and as a bonus, I'm going to ask for the mole fraction as well. I guess we can get the mole fraction first. I think that would be the easiest to calculate. So yeah, let's get the mole fraction. So the mole fraction of hydrogen, to be specific, because 0.94 grams of hydrogen versus 215 palladium, clearly hydrogen is the solute. So mole fraction of the solute is going to be moles of H2 over moles of H2 plus moles of palladium. Remember, it's moles of solute over moles of solution, and the solution is the solute plus solvent. In fact, I should probably mention that. Let's say this bar represents like the content of a solution. So if this bar represented an entire solution, I'd say most of it is going to be solvent. So I'll say this much of it is solvent. Can you see that? Yeah. And then the rest will just be the solute. Keep this image in mind, or at least remember solution is solute plus solvent. That'll be very, very important to remember when doing some of these conversions, specifically when converting between molality and something else. But yeah, mole fraction is going to be, let's see, moles of hydrogen. So I've got 0.94 grams, 2.016 grams per mole. I think we've done these conversions enough times by now that I don't have to write it out for you. 0.94 times 1 over 2.016 gives us about 0.47 moles over 0.47 plus, let's see, moles of palladium. So I've got 215 times 1 over 106.42 is about 2.02. Is about 2.02 moles. Okay, 2 decimals and 2 decimals. So after adding, we should still have 2 decimals. So that's going to be 2.49. 0.47 over 2.49. 2 sig figs over 3 sig figs is going to be 2 sig figs, so I'm going to round that to 0.19. So the mole fraction of hydrogen is 0.19 in this solution. Okay. They also wanted molarity, molality, and percent by mass. Percent by mass is also pretty easy to calculate, so let's do that one real quick. The percent hydrogen is going to be the grams of hydrogen, 0.94, over the grams of the whole thing, so 215 plus 0.94, and then that times 100%. Let's see, 215 plus 0.94 is just going to round to 216 because no decimal places, plus 2 decimal places rounds to no decimal places. So 0.94 over 216 and then times 100%. 0.94 over 216 and then times 100% gives me about 0.45 if I round it to 2 sig figs. And I guess I should switch to purple to stay consistent with what I've been doing. 0.44%. So even percentage-wise, really, really small amount. 0.44%. Not even 1%. Not even half of a percent. All right. And now let's determine... Let's determine molality next, because that's going to be easier than molarity. I'll save molarity for last. So molality we represent with a lowercase m. Molarity we represent with a capital M. Molality is a lowercase m. I was about to pronounce it molality. That would have been something. Well, I guess I just technically did. Molality. Could you imagine? I'm sure there are people who pronounce it that way. Probably people who don't speak English as their native language, in which case I can't really blame them. English is weird, and its rules are inconsistent. Kind of like chemistry, in a way. Kind of like chemistry. But yeah, molality, lowercase m, is moles of solute, which we already calculated earlier. So moles of H2 over kilograms of solvent. So, if I use lowercase m for, I'm just going to write out the word mass, because lowercase m is already taken for molality. Mass of palladium in kilograms. Okay, so that's going to equal moles of hydrogen we calculated earlier is 0.47 over kilograms of palladium. 215 grams of palladium. From grams to kilograms, all you have to do is divide by 1,000. You can write out the conversion factors if you don't believe me. But that's going to be 0.215 if you convert it to kilograms. And I guess, well, I didn't write the units in any of the other ones, but okay, moles over kilograms. And so we get 0.47 over 0.215 is going to be about 0.2, or maybe about 0.25 maybe. Wait. No, I did my math wrong. 0.47 over 0.215, rounding to 2 sig figs, gives me about 2.2 molal. 2.2 molal, or in other words, you can also say it's 2.2 moles per kilogram, which is probably easier to pronounce. I mean, molal is a weird word. And some people just pronounce it molal, which, I don't know, it sounds clunky. I emphasize the A and just pronounce it molal so that people know exactly what the word is, because if you pronounce it molal, people might mishear you and think you just mean mole, which, avoid the confusion. Just pronounce it molal, even if it doesn't sound the way you think it should sound. I mean, you would think because molar is pronounced the way it is that the A in molal should be pronounced the same way. But I'd rather not. I think it causes too much confusion. And finally, the molarity of the solution. So big M. Molarity is going to be moles of H2 over the volume of the whole solution. And can you read that? Yes. I keep on worrying that I accidentally shift the paper down outside the boundaries of the screen. So anytime I'm writing near the very top or the very bottom, especially the bottom, I frequently double check if what I'm writing can even be seen. Because we've already had videos where I've written things that you can't really see while I'm writing them. I'd rather not make that mistake too frequently. Okay, so the volume of the solution as a whole is going to be related to the mass of the solution as a whole via the density. So to convert between volume of solution and mass of solution, you need the density. So moles of H2 we already have, that's 0.47 moles. As for volume of the solution, remember the solution is the whole thing, solvent plus solute. So to get the volume of the solution, I need to use the mass of the solution. And the mass of the solution is, well, 215 plus 0.94, we did that earlier, rounds to 216 grams if you take hydrogen plus palladium together. And then if you take your 216 grams of solution, you can convert to the volume because every 10.8 grams, according to our given density, is equal to 1 milliliter of solution. Every 10.8 grams of solution is 1 milliliter of solution. 216 over 10.8 is going to give us exactly 20. But we have 3 sig figs here, so I would write that as 20.0. 3 sig figs over 3 sig figs should still be 3 sig figs. So 20.0 milliliters. And of course the volume of our solution needs to be in liters, so convert that to liters. That would be just divide by 1,000, so that's going to be 0.0200 liters. Did I do that right? Shift the decimal 1, 2, 3 places. Yeah. Okay. So gonna go ahead and plug that in down here. 0.0200 liters of the whole solution. And oh boy, this is going to be a really high molarity. 0.47 divided by 0.0200 is, if I round that to 2 sig figs, it's going to be 24. It's going to be 24 molar. Or 24 moles per liter if you prefer. Okay, 24 molar. That's a pretty high concentration. You wouldn't really expect that with solutions in water. But yeah, these sorts of high concentrations can happen. It's really because even though 0.94 grams seems tiny in comparison to 215, the molar masses are just so different that even 0.94 grams of hydrogen is still a lot of hydrogen in terms of actual number of particles. All right, so there's an example of that. Let's see. Do I want to do more examples of these concentration conversions? Well, I think we have some more that'll show up in some of the problems I prepared, so I guess we'll hold off for now. But I really do want to do problems where they give you one of these 4 concentrations and you have to convert to the other 3. So if they don't have those, then later on I'll just make some up. Okay, let's shift gears a little bit and talk about colligative properties. So, as I mentioned, molality is useful for predicting the physical properties of solutions, and some of those physical properties belong to a set of properties known as the colligative properties of solutions. Colligative properties of solutions. Yeah, let's write it down in the middle. My sense of symmetry won't allow me to write it over there. I don't know if that counts as OCD, but it is what it is. Colligative properties of solutions. So there are 4 different colligative properties that we want to focus on for solutions. Basically 4 observations that we have about solutions when compared to the pure solvent. So one of those properties is, or one of those observations, is the lowering of vapor pressure. Typically, when you dissolve stuff in a solvent, the vapor pressure goes down. Also, the boiling point goes up. So boiling point elevation. It's easier to boil pure water than it is to boil salt water. Boiling point elevation. Which is kind of related to the lowering of vapor pressure, and we'll talk about it. We've talked about the relationship between vapor pressure and boiling point before, so I hope you remember that stuff, but I'll quickly go through that relationship again. Maybe not in as much detail since I've done it before, and you can go back to, I think it was the previous video, for a more detailed explanation. But yeah, boiling point goes up, and the freezing point also changes. The more stuff you dissolve, the more the freezing point goes down. Freezing point depression is something we observe in a lot of solutions. And then there's the property of osmotic pressure. Osmotic pressure tends to go up as concentration goes up, as you dissolve more stuff into your solution. Let's see, so at this point it looks like I've been going for 3 hours, I think. Unless I'm misremembering the time. No, it feels like it's been 3 hours. Watch it be 2 after I start reviewing this video. Just goes to show how warped my sense of time is. Let's see. Where did I want to go from here? Well, I guess let's start with this diagram over here to illustrate the lowering of vapor pressure. So we talked about vapor pressure before. It's the pressure that the gas phase of a liquid exerts on the surface of the liquid when allowed to evaporate in a sealed container. So you've got pure water showing there on the left. Some of the water molecules have enough energy to escape the liquid phase and go into the gas phase. And so you get those water vapor molecules up there in the top. They're kind of free to move around. They bounce off of the walls of the container, and some of them might collide back into the water. That's why you have those arrows pointing down for some of the particles. They might go back into the water and get captured and become liquid again. But at some point, you reach basically the maximum amount of water vapor. You reach the maximum amount of vapor because at that point, the amount of water that's evaporating is equal to the amount of water that's unevaporating, that's condensing and going back in and getting captured by the liquid again. So at that point, even though there's still changes going on, even though you still have liquid turning into gas and gas turning into liquid, on a macroscopic scale, if you zoom out and just look at the big picture, then in the big picture of things, nothing is really changing anymore. The total amount of vapor versus the total amount of water that's still liquid isn't going to change, even though individual particles might still be changing. The overall contents of that container don't change. Okay, so once you reach that point, whatever the pressure of the gas is in the container, that's the vapor pressure. So you can think of it as how much the gas on the top presses down on the liquid at the bottom, but also you can think of it as how strongly the liquid at the bottom pushes up against the gas on top. And in an aqueous solution, where you have some dissolved particles in there, well, you get less gas because less of the particles can actually make it all the way to the surface without physically bumping into those dissolved particles. The dissolved particles act as a sort of obstacle that's in the way, and they make it so that it's not as easy for water molecules to go up into the gas phase. And as a result, the total amount of gas you have at the end, when you've got some solute in there, is going to be lower when compared to just the pure water, when compared to the pure solvent. And so you get a lower vapor pressure. Less moles of gas leads to less pressure. We know that from studying our gas laws. And less vapor pressure means less or lower, less vapor pressure means that it's not going to boil as easily. If you remember in the previous video, we talked about how the boiling process is kind of this competition between the pressure of the particles that are trying to go up and turn into a gas. So I would call this P vape, the vapor pressure, versus the atmospheric pressure, versus whatever external pressure you've got. I'll just say it's atmospheric. So the higher the atmospheric pressure is, the harder it will be for gas particles to come out of the liquid. Until, of course, the vapor pressure rises so high that it's equal to the atmospheric pressure. And the way you do that is by increasing the temperature. So P vape goes up when temperature goes up. And when the temperature goes up high enough that the vapor pressure is equal to the outside pressure, when P vaporization is equal, or well, P vapor is equal to P atmosphere, or whatever the external pressure is, then you're at the boiling point when T equals T boiling. So yeah, boiling happens when the vapor pressure is high enough to completely overcome the atmospheric pressure, and in that case there's nothing blocking these liquid molecules from turning into gas. There's nothing preventing them at all. Everywhere below that temperature, only some of the gas particles will succeed in climbing out of the liquid phase and into the gas phase. Did I call them gas particles just now? Whatever I said, I guess I'll correct it in a pinned comment if need. Well, no, since I'm calling it out right now, I don't think there's a need for a pinned comment on it. But if I called them gases while they were still in the liquid phase, then that was a mistake on my part. I've lost my train of thought. Where was I going to go next? So, yeah, if the vapor pressure is lowered as a result of having solute particles in the way, then in order to raise the vapor pressure high enough to reach the boiling point, now you need to raise the temperature even more. Now you need to raise the temperature even more, because if you have solute particles in there, the vapor pressure starts even lower than it normally would. So you have to raise it more, which means you need to increase the temperature more in order to reach the boiling point. And that's why, as a result of a lowered vapor pressure, you get boiling point elevation. The boiling point is higher as a result of that. Before we dig into boiling point elevation, maybe we should talk a little bit about using boiling points to separate different liquids. Or maybe that's awkward placement. You know what? No, let's talk about it right now. So, when it comes to miscible liquids, for example, alcohol and water, let's say you have alcohol dissolved in water and you wanted to separate them. If you had a solid dissolved in water, it would be easy. Just evaporate all of the water and the solid would remain inside of the container and you'd get the solid out. And I guess you could collect the water vapor in some sort of container and recondense it if you really wanted to keep the water. But yeah, separating a solid from a liquid solvent is pretty easy. What about when you have a liquid dissolved in liquid? In that case, we use a process known as distillation to separate them, and distillation is based on the difference in boiling points. So the idea is that you heat up the solution, but you don't heat it up too quickly. You heat it up so that you reach the boiling point of whichever one boils more easily. And you let that part of your mixture evaporate, and you collect it. So that green solution, that sample mixture as it's labeled, some liquid is going to evaporate out of it. It goes up through this tube, and some of that vapor will eventually creep into that slanted tube that you see in the blue. And that blue tube, what is basically going on inside of it is water is being pumped through it, cold water. And when your evaporated substance comes into contact with, well, it doesn't directly contact the cold water, but it contacts the glass that's touching the cold water, it will cool down and it'll condense, and it'll start dripping down into that other flask on the far right. And that way you can collect whatever evaporated first. You evaporate it out, and then you condense it back into a different flask. And of course, once you've waited long enough that you're sure you've evaporated out all of the, let's say alcohol. I think alcohol boils at a lower boiling point than water. Let's say that's alcohol and water. Once you've collected all of the alcohol, or you're sure you've been running it long enough to collect all the alcohol, you stop and you're done. You've got the alcohol separated off from the water, or whatever your mixture just so happens to be. And by the way, for that cooling tube that has the water being pumped through it, as you can see with the blue arrows that are in the middle of that diagram, the water goes in at the bottom and comes out at the top. And you definitely don't want it to go in at the top, because gravity will kind of help the water go down faster, and some of the water might escape from the bottom outlet before it fills like the bottom part of that, condensing section. So yeah, you want to hook it up where the water goes in from the bottom, because that way you guarantee that the bottom gets filled before the water reaches the top and comes out the top. So that's something that you're going to want to remember if you're working in the lab. Oh boy, do I have stories about when my classmates in my organic chemistry lab specifically would hook these things up completely wrong. Oh goodness, there was a reason why I didn't continue majoring in chemistry and just settled for the minor, and a big part of it was I couldn't stand the classmates I had in chemistry. But that's a rant that you guys probably don't care about. Let's go back to... Oh, actually, there's one more thing I need to show you. So, distillation, so simple distillation works when you've got two things with really different boiling points, or boiling points that are different enough that you can actually separate them. But sometimes you've got a lot of things to separate. Sometimes you've got a lot of liquids to separate, especially with something like crude oil. So for that, they have something that's a little bit more elaborate, but it's the same idea. It's called fractional distillation. We call each of the individual things that we want to separate out fractions, and so it's called fractional distillation. So in that diagram, you see they have some something like crude oil, and it starts out at the bottom. They start vaporizing it. The first thing to evaporate, I guess, is... Wait, do they have this organized top to bottom or bottom to top? Okay, yeah, the things that evaporate the best are going to climb up to the top. So refinery gas, then the next best thing is gasoline, then I guess it's pronounced naphtha, kerosene, diesel oil, and fuel oil. So each of them are separated from each other based on their different boiling points. It's really just the same thing as regular distillation, but they just want to do it all in one go instead of separating them one substance at a time. So yeah, that's fractional distillation, just kind of an FYI thing. Okay. And with that, I think it's time to talk about both boiling point elevation and freezing point depression in a little bit more detail. So, Boiling point elevation and freezing point depression. For boiling point elevation, we've already explained how it works. It's because of the lowered vapor pressure. You need to raise the temperature even more to get the vapor pressure up to the atmospheric pressure, or whatever surrounding pressure you've got on your solution. And it turns out that the amount of increase in the boiling point is directly proportional to the amount of solute that you put in. In fact, it's directly proportional to the molality, the moles per kilogram concentration. So we say the change in the boiling point, or the boiling point elevation, is equal to some constant, which we usually call Kb for boiling. I'll make it a capital K so that we don't confuse it with the Boltzmann constant, times the molality times something called I. This we'll talk about some more. This is called the Van't Hoff factor. We'll talk about it some more later, but basically it has to do with whether the solute is an electrolyte or a non-electrolyte, and if it is an electrolyte, it depends on whether it's a strong electrolyte or a weak electrolyte. We'll dig into it later, but for now, let's just assume that I equals 1 until further explained. Assume I equals 1 until stated otherwise. Most textbooks don't bother mentioning the Van't Hoff factor this early on. They keep it towards the end of the chapter, but I feel it's important to bring it up earlier. So there it is. So that's the boiling point elevation. Freezing point depression works in pretty much the same way. So delta Tf is equal to some constant, Kf, times the molality times the Van't Hoff factor. And I guess I should put absolute value bars around these. But yeah. As for freezing point depression, why is the freezing point lower? Why is a solution harder to freeze than a pure solvent? Well, let's look at it on a molecular level. Let's say I have, I don't know, sodium chloride versus pure water. So let's say I've got pure water just draw a couple of random water molecules here and there. Let's see. And I guess I'll draw one more for the pure water. Okay, actually, you know what? I'll do 2 in 1. Yeah, I was going to draw 2 separate things, but I think I can do a 2 in 1 sort of deal. Okay, so in a solid, the particles are arranged in such a way that they're really close to each other. So to freeze water, you need to get the water molecules to get really close to each other. And they can do that. You've frozen water before. You can make ice. It's not that hard. But what if I had some sodium chloride ions in between? What if I had some sodium ions and some chloride ions in between? Well, then it's not going to be as easy for the water molecules to get close to each other because the ions are in the way. Now the water molecules have to get closer to each other while having these ions stuck in the middle. So they can get close, but they can't get as close to each other as when the ions are not in the way. And that's basically it. They don't even have to be ions. Again, you can dissolve other polar substances in there. You can dissolve alcohol, you can dissolve chloroform, and so on and so forth. But yeah, having solute particles in the way, and I guess I didn't really draw their sizes to scale, but having them in the way makes it harder for the water molecules to get closer to each other. And so you need to cool things down even more to get the solution to freeze. And that's basically it. That's basically the gist of it. That's why the freezing point goes down while the boiling point goes up. So the thing to remember is the more stuff you dissolve in there, the harder it is to freeze and the harder it is to boil. Both processes are harder to do. Okay, so what is this K constant in these two equations? The boiling point elevation constant and the freezing point depression constant. Basically, they just depend on what the original solvent was. Here's a chart that lists a couple of them. We're typically going to work with water, and of course, water's normal boiling point is at 100. Its boiling point elevation constant is 0.512 degrees Celsius per unit of molality. Its freezing point by default is 0 degrees Celsius, but it will lose 1.86 degrees Celsius from its freezing point for every 1 unit of molality when you make a solution out of it. And you can apply that same thinking to hydrogen acetate, benzene, chloroform, nitrobenzene. I am surprised that they don't have alcohol listed here, but okay. Anyway, for water, which is what we're going to be dealing with for the most part, 0.512 and 1.86 are going to be the numbers to use. So I guess let's do a crude example. I'll just give you the, let's say we've got, I'm not going to make it too calculation heavy. Let's say we dissolve 2.0 moles of sugar in let's say, well, let's just keep it simple, 1.0 kilograms of water. Okay, let's suppose I take 2.0 moles of sugar in 1 kilogram of water. What is the new freezing point and what is the new boiling point of that solution? Let's calculate the molality. So molality is just going to be moles of solute, so 2.0 moles of sugar over kilograms of water, which is 1.0, and 2.0 over 1.0 is 2.0. Isn't that nice? 2.0 moles per kilogram, or 2.0 molal. Okay, so now that we have that, we can plug it into here and here, and we already have the elevation and depression constants. Let's go ahead and put them in here. So delta T boiling, lowercase b, not capital, delta T boiling is equal to, the boiling constant was 0.512 times a molality of 2.0 times a Van't Hoff factor of 1, exactly 1, so don't count this as 1 sig fig. Okay, so 0.512 times 2.0 times 1 is going to be 1.014, and rounded to 2 sig figs, I guess, would just be 1.0. Okay, so that's 1.0 degrees Celsius? No, Celsius degrees of change. So that's boiling point elevation. What about freezing point depression? So that's going to be 1.86 is Kf for water times 2.0 times a Van't Hoff factor of 1. 1.86 times 2.0 is going to be 3. It looks like 72, which just rounds to 3.7 Celsius degrees. Okay, but those aren't the new boiling and freezing points. Those are the changes in the boiling and freezing points. So the boiling point increases by 1 degree Celsius. It's normally 100, so it's 100 plus, or I guess 100.0 plus 1.0 gives us the new boiling point of 101.0 degrees Celsius. The freezing point decreases by 3.7, so water is normally 0, subtract 3.7, and you've got, well, 0.0 minus 3.7 gives you a freezing point of negative 3.7 degrees Celsius. So in other words, this sugar solution at normal freezing temperature at 0 degrees Celsius will still be liquid. It'll still be liquid, which has an important application. There's an important application to that. Salting of roads. Yeah, for those of you that live further up north, I don't know which parts of the world some of you viewers are coming from, but I'm assuming most of you are American or Canadian or maybe even British. But for those of you who live in countries where you actually get to see snow, you might get so much snow that the government comes in and has these trucks that start, putting salt all over the road. And the reason for that is because if you dissolve salt into the ice, then you will lower its freezing point. And you'll lower it so much that it'll be below the actual temperature on that day. And so the ice, the snow, will melt much more easily. And that helps improve road safety. Of course, if you really want to improve road safety, eliminate the human drivers. Soon, self-driving cars will be here. Well, I mean, they're already here, but, they're still in the testing phase. And yeah, they have car crashes, but they have less car crashes than the average human, so at the end of the day, I think self-driving cars are inevitable. Can you imagine a world where nobody knows how to drive? That would be something. Anyway, that's road salting. So, road salting is all about freezing point depression. If you lower the freezing point enough, then you can keep the ice as a liquid, which makes it safer to drive on. Okay, so that was boiling point elevation and freezing point depression. And I guess we can also talk about how this has an effect on our phase diagrams. So this phase diagram is specifically about liquid solutions where the solvent is a liquid and the overall state of the solution is liquid. But yeah, you remember phase diagrams from the previous video. Increasing the concentration, dissolving stuff in your liquid, will modify the phase diagram a little bit. So I think it's kind of self-explanatory. There's the freezing point depression and boiling point elevation illustrated by those dotted lines. So you can see between liquid and solid, the dotted line is a little further to the left towards lower temperatures, whereas for boiling point, the dotted line is a little further to the right where you have higher temperatures. And they also make a note of, in the middle of the diagram there, the change in pressure, which is hinting back at the lowering of the vapor pressure. But yeah, that's something you can study and look at on your own. It's not brought up all that much. In fact, I don't think I've ever seen it brought up in a typical chemistry course. So really this chart is kind of just an FYI. You can study it and make sense of it. It's not that hard to understand. Where do I want to go next? Well, I guess we've talked about all of the colligative properties at this point except for osmotic pressure. So yeah, let's talk about osmotic pressure. Let's switch to another page here and talk about osmotic pressure. Oh, and by the way, for the lowering of vapor pressure, there isn't really an equation that we need to know. So if you're wondering where's the equation for that, we don't have one. At least we don't have one that's simple enough for a typical general chemistry course. So no equation for that, but we do have an equation for osmotic pressure of a solution. But first we need to talk about what osmotic pressure even is. And to start, we need to talk about what osmosis even is. So let's start with osmosis. Those of you who've taken biology probably already know this, so this won't sound new to you, but osmosis is a process by which typically liquid, but I don't think it has to be liquid. I'll just stick with liquid for now because that's the typical example. A process by which liquid at lower that's not how you spell lower, at lower concentration moves to a region of higher concentration through a semi-permeable membrane. Through a semi-permeable membrane. Oh my God, that's a lot of writing. Okay. So basically, imagine if you had I guess I'll draw it over here. Imagine if you have this sort of filter thing that has really, really, really tiny holes in it. And you have, let's say, just pure water on this side. So pure water. And on this side, you have not so pure water. So you'll have some dissolved particles in there. I guess I'll do them in purple, or whatever this color is. Yeah, that looks pretty purple to me. Okay, so, and maybe I should draw these bigger to help emphasize the point. Yeah, I'll draw them bigger. So if I didn't have this membrane separating them, if I didn't have this filter thing or whatever it is separating the two from each other, then what would normally happen is dilution. What would normally happen is I would mix this with this, and the solute particles would just be even more spread out, and the concentration would go down. But that can't happen here because this membrane only allows the water molecules to go through. So the water molecules can go through just fine. The holes are big enough for the water molecule, but they're not big enough for whatever this solute molecule is supposed to be, or if it's a molecule at all, maybe they're ions. But yeah, it just so happens to be the case that the water can go through, but the solute cannot. And so what will happen is overall, more of the water from the pure water side is actually going to go to the not so pure water side, and the concentration of this stuff will be lowered that way, not by decreasing and spreading out the solute, but by increasing the amount of solvent. More solvent will migrate to the right than to the left, and the concentration of this solution will decrease as a result. And yeah, the driving force behind this is what's known as osmotic pressure. So if we take a look at this diagram over here, you've got, on the left, you start with a pure solvent, so pure water, for example, and a solution, some sort of maybe salt water. And at first, they start out, on equal footing, at equal elevations and all that. But there's a semi-permeable membrane down there in the middle that's standing between them. So pure solvent will move over to the right, and as a result, the volume on the right will start to increase. The volume on the right will start to increase, and its height will start to go up as well. And there's this pressure that builds up as a result of that. We've talked about this idea before. If you remember when we were covering gas laws, we talked about the barometer and how the higher the liquid level was in the barometer, the more pressure it was exerting. Basically the same idea over here. The elevation in the liquid level on the right compared to the one on the left, the higher it goes and the greater the density of the liquid on the right, the more pressure it exerts on the right-hand side. You can also, actually, I guess since we're talking about gas laws, let's also talk about the the total pressure above both sides, because I think that can help explain a little bit of what's going on. So you might also remember, actually, did I talk about this, or was that for a physics topic? I feel like I remember explaining this before, but it might have been in a tutoring session with one of my physics students. I don't remember if I talked about this in a chemistry video, but if I did, it was in the gas laws video for sure. Okay, and we've got our membrane down there. So we've got that, and we've got that, and I guess I'll just draw some solvent particles there and some over there. And let's see, some solute particles Yeah, I think 4 is enough. Okay, so on both sides of this thing, you've got atmospheric pressure. On both sides of this thing, you've got atmospheric pressure, so that's going to cancel out. But also you've got vapor pressure. Yes, the vapor pressure is the pressure with which the gases that are trying to, evaporate push up on the atmosphere, but it's also the pressure by which the already evaporated gas pushes down on the solution. Gases actually push in all directions, so down and right and left and up and down and every which way. So pressure atmospheric plus you'd also have the vapor pressure. And over here, same thing. You'd also have the vapor pressure. But if you remember, vapor pressure goes down when you have more solute particles. So this vapor pressure is less than this vapor pressure. So the total pressure on the right-hand side is less than the pressure on the left-hand side. And so the water level can go up higher on this side because there's less total pressure pushing down on it. And yeah, so that difference in height, that height difference right there, is going to be proportional to the pressure change, which we call the osmotic pressure. So that change in height is proportional to osmotic pressure, which we don't represent with a P. Interestingly enough, osmotic pressure is represented with a capital pi. Pi from the Greek alphabet, except it's a capital pi. So, it's just drawn bigger. It doesn't look too different from the pi you already know. Not 3.14, not pi from your math class. In this case, they're using pi as a variable, which I think is kind of stupid, to be honest, but it is what it is. So they use pi to represent osmotic pressure. But yeah, that's the gist of it. So that extra pressure over there, that's the osmotic pressure. I think they have a diagram here. Yeah, so here's this other diagram that they show. Basically, they define osmotic pressure as the amount of extra pressure you have to put on the right side to get the heights to be equal again. So they've added this heavy disk thing. They've just put it in there to apply pressure onto the right side to keep it from, rising any higher than the left side. And whatever that pressure is, that's the osmotic pressure. That's capital pi of the solution. And yeah, that's the idea behind osmotic pressure. You don't really need to remember most of that, so if you blank out on the last, 5-10 minutes of this video and you just completely forget it, you can probably get away with it. I'd encourage you to try and remember and understand conceptually what's going on, but if all you care about is what'll be on the test, you're probably not going to be tested on this. Then again, it depends on who your teacher is. Formulas. So there is a formula for osmotic pressure. There is a formula for it. And the formula is, it's actually based on the ideal gas law. It's based on the ideal gas equation. So ideal gas equation says PV equals nRT, which we've seen enough times already. Replace the P with a pi. because that's just how we do it for osmotic pressure for whatever reason. So pi V equals nRT. Nothing changed really, it's just the naming. Divide by volume. And so you get pi equals nRT over V. I'm going to write it as N over V times RT, and I think some of you already see where this is going. N over V, moles over liters. That's molarity. That's molarity. So it turns out osmotic pressure is equal to molarity times the ideal gas constant times the absolute temperature times the Van't Hoff factor. Don't forget the I, it also affects osmotic pressure. So let me see. Since this is going to be in moles per liter, the ideal gas constant is either going to be in liter torrs per mole Kelvin or liter atmospheres per mole Kelvin, depending on whether you want to get your pressure in torrs or atmospheres. But yeah, whatever version of the ideal gas constant you use, it has to have liters in it because your molarity is in moles per liter. So that's something to keep in mind. You're probably not going to be asked more than 1 or 2 questions about osmotic pressure in your whole entire course, but there it is. Okay, so yeah, that's osmosis and osmotic pressure. For you biology enthusiasts out there, just one more little tidbit about osmosis. So it is possible to drink too much water. I think sometimes it's called hydrogen poisoning. And if you do drink too much water, this is what's going to happen to your cells. If you see on the far left image there, those are not normal cells, they're overly bloated, and that's because the cells in your body, in this case I guess they're red blood cells, they will have basically this sort of soup of all sorts of stuff, proteins and whatever else is dissolved in there inside the liquids in your cells. If there's water outside of your cells, well, the walls of your cells are going to be these semi-permeable membranes. They can let the water in without letting the dissolved stuff inside the cell out. And so water will go in, they'll start bloating up, and they could rupture. And that's what you see going on the left-hand side. So drink enough water, but don't drink too much water. Basically, only drink water when you actually feel thirsty. Don't listen to those people who say you have to drink X amount of glasses of water every day. If you're forcing yourself to drink water when you're not feeling thirsty, it's probably a bad idea, unless, you've been diagnosed with some weird illness and your doctor told you to. Of course, the exact opposite can also happen. So if you, for example, consume too much salt, for example, then all of a sudden the concentration outside of your blood cells is higher than the concentration inside your blood cells, so water will move out of your blood cells and into, I guess, your blood plasma? Is that the correct terminology? I'm not much of a biology person. I just know things here and there. Maybe I should read up on my biology. But in any case, you see in that far right image, the cells just kind of shrivel up and deflate. And that's no good either. So you really want to keep the concentration of dissolved substances in your blood at normal levels, not too high, not too low. But yeah, that's not really all that relevant to chemistry. It's just there for the biology students, so I hope I made you happy. Now I think it's finally time to start talking about Van't Hoff factors. Okay, so what's going on with the Van't Hoff factor? So earlier we did 2 moles of sugar and 1 kilogram of water. And sugar has a Van't Hoff factor of 1. Now, if I did 2 moles of sodium chloride in 1 kilogram of water, I would notice that the boiling point elevation and freezing point depression, and also the osmotic pressure, if I bothered to calculate it, would actually be double what I got in the original problem. Why? Why? Because the effects of boiling point elevation, freezing point depression, lowering of vapor pressure, and osmotic pressure, they all depend on just the raw amount of dissolved particles. They depend on the raw amount of dissolved particles. So if I put in something like sodium chloride, then I'm going to get 2 particles of sodium chloride for every formula unit of sodium chloride that goes in there. So if I put in 1 mole of sodium chloride, I get 2 moles of dissolved particles. I get 1 mole of sodium ion plus 1 mole of chloride ion. So in total I get 2 moles. So you could say the total molality is going to be 2 moles of ions over however many kilograms of solvent you have. But usually we give the molality of the substance as a whole rather than just the individual ions, so instead we make up for it by just multiplying by the amount of ions per particle or per formula unit. And that factor that we multiply by is what's known as the Van't Hoff factor, the little I. So for sodium chloride, you can expect little I to be equal to 2. For something like iron 3 nitrate, which we saw earlier, iron 3 nitrate, that would have a Van't Hoff factor of 4 because it splits up into 4 different particles, 1 iron ion and 3 nitrate ions. But of course, it's not quite perfect. We are kind of making assumptions here. So let's take a look at this chart that lists a bunch of Van't Hoff factors. So for non-electrolytes, the Van't Hoff factor is a perfect 1, always. So for sugars like glucose and sucrose and fructose, the Van't Hoff factor is 1. For something like sodium chloride, which is a strong electrolyte, you expect it to completely separate into ions, so you would expect the Van't Hoff factor to be 2. In reality, it's 1.9, so, I would still just use 2 to simplify calculations, but it's not perfect. Sodium chloride does not completely separate into ions. We'll talk about that a little bit more when we discuss one of the equilibrium chapters, not the first one, though. Probably not the first one. But yeah, once we start talking about equilibrium, we'll dig into that a little bit more. But for now, we'll just assume we live in a perfect world where sodium chloride and all of these other strong electrolytes do dissolve completely. Magnesium sulfate is kind of surprising. You would expect it to yield 2 particles per unit of MgSO4, but it gives you 1.3. Magnesium chloride dissolves pretty well. You expect 3, you get 2.7, so pretty good. Iron 3 chloride, it looks like you're getting about 3.4. But yeah, for strong electrolytes, just assume they completely dissolve for now and completely separate into ions. And for non-electrolytes, of course, they're not going to separate at all. And then for weak electrolytes, you're going to get something that's in between. So if I had something like acetic acid, for example, acetic acid, I think we did an example involving acetic acid earlier. Let me see if I can find the page where I did that, because I'm pretty sure I did it somewhere around here. Where did I? Ah, there it was. So yeah, if I have 100 molecules of acetic acid and 5 of them break up, yielding 5 hydrogens and 5 acetate ions, and then 95 of them remain intact, well then, what's the Van't Hoff factor in this case? If 100 molecules turned into 95 plus 5 plus 5, then that's 105 per 100, or 1.05. 105 over 100, so I get 1.05 dissolved particles per particle of acetic acid. So acetic acid would have a Van't Hoff factor of 1.05 in my earlier example, but in general, we would say acetic acid can be anywhere between not splitting up at all, so just a Van't Hoff factor of 1, and between completely splitting up into hydrogen ions and acetate ions, which would yield a maximum of 2. So in general, we'd say the Van't Hoff factor for something like acetic acid is between 1 and 2. And yeah, for weak electrolytes, you're not expected to know the Van't Hoff factors. They will either give you the Van't Hoff factor, or they will give you everything else and ask you to calculate the Van't Hoff factor. So you're not expected to just know Van't Hoff factors for weak electrolytes. You will be given the information you need to determine that if necessary. So for the most part, you're going to be dealing with non-electrolytes and strong electrolytes, and it's very, very, very common for students to forget about the Van't Hoff factor when they're dealing with a strong electrolyte. I see a lot of students, they look at something that's asking them about a solution of sodium chloride, what is its new boiling point, what is its new freezing point, and they'll calculate it the same way we did with sugar. They'll completely forget that sodium chloride has a Van't Hoff factor of 2 because, well, the problem itself doesn't mention it. You kind of just have to notice it. But yeah, most ionic compounds, if they're going to dissolve in water, then you can assume they're going to give you strong electrolytic solutions. So you can assume they dissociate completely. Let me see. So I guess we have a little bit of an explanation for the incomplete dissociation. I guess we don't need to wait until equilibrium to talk about it. So there's an illustration showing how incomplete dissociation could happen. So yeah, something like potassium chloride, you expect to get a Van't Hoff factor of 2. You get something that's slightly less, and the reason is because the water molecules do a pretty good job separating the cations and anions from each other, but it's not always perfect. Some of the ion pairs do stay pretty stuck together, and the water just can't drive a wedge between them. So it can happen. Some ions do remain paired, but usually it's to a negligible degree. So yeah, it can happen. Just be mindful of that when you're working on a project for some professional lab, but for academic purposes, for school purposes, I think assuming you live in a perfect world is fine for the time being. All right, I think it's time to go back to some more problems. And then after we do some more of these, we will talk about colloids and suspensions real quick, and then we'll wrap things up. Okay, I think we were on this page, right? Yeah, looks like it. So 26 I didn't like, but I gave you the gist of what they want you to do. I don't think we need to go through it. 27, what is the microscopic? Okay, it relies on a figure that I don't have ready, so we'll skip that. 28, sketch a qualitative graph of the pressure versus time for water vapor above a sample of pure water and a sugar solution as the liquids evaporate to half their original volume. Interesting. This one might require a little bit of thinking. So we've got pure water and sugar water. Pure water and sugar water. And we're lowering both of them to half of their original volume. So I guess that'll be about half as high. And that should do that. And then for the sugar water, let's just include some green particles to represent sugar. Let's see. So they said sketch a qualitative graph of the pressure versus time for water vapor above a sample of pure water and a sugar solution as the liquids evaporate to half their original volume. Okay, so for the pure water, I guess as you actually wait. Water vapor as the liquids evaporate to half their original volume. Evaporate and not boil, right? Okay. If they evaporate and don't boil, then the vapor pressure of the water is just going to stay constant. The vapor pressure is going to be something less than the atmospheric pressure, and it'll just stay as what it is. And yeah, it'll just stay constant. Okay. And in the case of the sugar water, it's a little bit different because, well, first of all, it's going to start lower. It's going to start lower than the original one. So let me just draw a dotted line there to clarify that we're starting at a lower pressure. But the lowering of the vapor pressure doesn't just depend on the amount of solute particles. It also depends on the ratio of solute particles to solvent particles. So as more and more solvent particles evaporate, the concentration of the solute is going up, and so that lowering effect is also increasing. So it doesn't stay at a constant pressure. The pressure does go down, but it doesn't just go down in a straight line. So the pressure is not going to just go down like this. It's going to go down at a rate that increases. So it's actually going to go down a little at first, go down some more, go down even more, and yeah, it'll take a sharp downward turn. And I know I basically made it go into the negatives there, but assuming the pressure is still positive here, so maybe set this pressure to something like, I don't know, let's set it to 1 atm, and let's say down here is like 0.1 atms or whatever. But yeah, the pressure doesn't just go down, it goes down at an increasing rate. So the rate at which it goes down gets faster. Goes down a little bit between here and here, then goes down a lot in an equal period of time later on. Probably too high level for most general chemistry courses, but for those of you that are mathematically oriented, I think you might find this intriguing. So there it is. Okay. Next up, we've got 29. A solution of potassium nitrate, an electrolyte, and a solution of glycerin, a non-electrolyte. That's them telling you to remember your Van 't Hoff factors. Both boil at 100.3 degrees Celsius. What other physical properties of the two solutions are identical? Okay, so if they both have the same boiling point of 100.3 degrees Celsius, that means their boiling point elevation is 0.3 degrees, which means that whatever the concentration of the glycerin was, the concentration of the potassium nitrate must have been half as much to achieve the same boiling point elevation. And then they're asking what other physical properties are identical? All the colligative properties. The lowering of vapor pressure, the oh, wait a minute. I just remembered we forgot to mention Raoult's law. We do have an equation for lowered vapor pressure. I'll go over that soon. I just remembered it. I had a feeling I was forgetting something. Anyway, all of their colligative properties are identical. Boiling point, freezing point, osmotic pressure, and vapor pressure are going to be identical. Before I forget, let me go over Raoult's law real quick. Okay, forget what I said about the vapor pressure equation. We actually do have a formula, except the problem is the formula doesn't work all that well. We do have a formula, but it doesn't work all that well. We have something called Raoult's law. I think I'm going to misspell this. Was it U-O-L-T or O-U-L-T? I get the feeling it was U-O-L-T. Raoult's law, which depends on mole fraction. And I should have realized it when when I noticed that we hadn't used mole fraction yet. So Raoult's law says that the vapor pressure of a solution, is equal to the vapor pressure of the solvent times the mole fraction of the solvent. Usually this is written as P equals X of A times P of A, where A is the solvent. So the vapor pressure of water, for example, let's say at some temperature the vapor pressure of water is 20 torrs. Let's say at some point the vapor pressure of water is 20 torrs at some temperature. If you dissolve stuff in the water such that the mole fraction of water is, let's say, 0.8, if we dissolve stuff in the water and we take the moles of that stuff plus the moles of the water, and we take the moles of the water divided by the total moles, and we get 0.8. If we get X of water to be 0.8, 8 moles of water for every 10 moles of water plus other stuff. Then you can say that the vapor pressure of the solution, is going to be 0.8 times 20, which is 16 torrs. And yeah, that's basically it. It's really simple. The problem with Raoult's law is that it assumes you are working with an ideal solution. And most solutions are non-ideal, so not really all that useful. But yes, you can calculate the new vapor pressure of a solution, assuming you know the vapor pressure of the solvent before you dissolved stuff in it. What about liquid-liquid solutions? What about something like alcohol and water? In that case, you would calculate the new pressure for the alcohol and the new pressure for the water and add them up. So I guess I'll do that on a separate page. If I have a solution that contains, I don't know, 20 moles of alcohol and 80 moles of water. Let's say we've got 20 moles of, let's say our alcohol is ethanol this time. Let's say you've got 20 moles of ethanol and 80 moles of water. And you calculate their mole fractions. I made the numbers easy, so the total moles is 100. Mole fraction of ethanol would be 0.2. X of ethanol, I'll just abbreviate it, Eth, is 0.20. And the mole fraction of water is 0.8 again. If you know the normal vapor pressures of ethanol on its own and water on its own, then what you would do is you would say the total new vapor pressure of this solution is equal to the mole fraction of ethanol, the mole fraction of ethanol times the usual vapor pressure of ethanol, I can't talk today, plus the mole fraction of water times the normal vapor pressure of water. And whatever those normal vapor pressures are going to depend on the temperature in a not so simple relationship So you're really just going to have to look them up in data tables, but you're probably never going to be asked to do something like this. For water, solutions of solids in water, yes, but for a liquid in a liquid, probably not. Just there it is if you need to know it. So yeah, that's Raoult's law for calculating changes in vapor pressure. The less your solvent, the less percentage of your solution is solvent, that's the percentage reduction in vapor pressure, basically. If you have a liquid that's 100% water, then it'll have 100% of the vapor pressure of water. If you have something that's 80% water by moles, not by mass, then it'll have 80% the vapor pressure of water. That's basically the intuition behind it. But again, this only works for ideal solutions, so, you know, it's not perfect. You're not going to make accurate predictions for real-world applications using Raoult's law. Not without modifications, anyway. Let's see. So, going back to our problems, I think we stopped at 29, so 30. What does 30 say? What are the mole fractions of phosphoric acid and water in a solution of 14.5 grams of phosphoric acid in 125 grams of water? Outline the steps necessary to answer the question and answer the question. I don't know why they bother with this, but okay. In step 1, they ask you to outline the steps, and in step 2, they ask you to answer it. They could just ask you to answer the question, and that would imply that you have to outline the steps, but who am I to nitpick over the problem formats in this book? But yeah, calculating mole fractions isn't something we are strangers to. We've seen this before. Okay, so I think we'll pass on that. 31. What are the mole fractions? Ooh, this one I think I do want to do. I think I do want to do this one, because this one is a concentration conversion. Yeah, I think I want to do this one. So, 31. What are the mole fractions of nitric acid and water in a concentrated solution of nitric acid that is 68% nitric acid by mass? Okay, and I'm also going to add to this problem. So we're given 68.0% nitric acid in water by mass. And I'm just going to make up a density for this. So if you go on Wikipedia or something and you look up the actual density of 68% nitric acid in water and you tell me that I was wrong, well, I'm making it up, so of course it'll be wrong. It would be amazing if by coincidence it just turns out to be exactly right, but I'm going to say the density of this thing is 1.24 grams per milliliter. Let's just say that's the density of this solution. We need some sort of density in order to answer some of the questions that I'm going to add on to this problem. So first thing they wanted was the mole fraction of nitric acid. But I also want the molality and the molarity. I want all three. Concentration conversions can be really difficult if you don't know what you're doing, but with enough practice it will become very easy to figure out what you're doing as you go. So let's see. If it's 68% nitric acid by mass, then here's what we need to do. First, I'm going to assume I have 100 grams of solution. I'm going to assume I have 100 grams of solution. That assumption would then mean that I have 68.0 grams of HNO3, and the remaining 32.0 grams would be water. Okay, based off of that, I can now calculate moles for each. So let's go ahead. Molar mass of water is 18.02 approximately, so 32.0 divided by 18.02 is going to round to about 1.78 moles. So 1.78 moles. And molar mass of nitric acid, I don't know off the top of my head, so periodic table. If you want to follow along, that's great. I'm just going to do it on my own. We've seen this enough times. Well, we haven't really done calculator stuff in a long time. So maybe you know what? No, I'll just assume you remember how to do it, and if you don't remember, you can go back to the old videos. 68.0 grams, so HNO3, we've got 1.008 plus nitrogen is 14.007. Well, actually no, I'll do 2 decimal places, so 1.01 plus 14.01 plus 3 times 16.00. And that's 63.02. 63.02 grams per mole. So 68.0 divided by 63.02 gives me about 1.08 moles of nitric acid. Okay. There we go. So mole fraction of HNO3 would be 1.08 over 1.08 plus 1.78. 1.08 over 1.08 plus 1.78, which equals 1.08 divided by, well, let me add these first. 1.08 plus 1.78 is 2.86, and then 1.08 over 2.86, 3 sig figs, that's 0.378. 0.378. And mole fractions do not have units, as you may recall. Molality and molarity. Which do I want to calculate first? I guess molality would be easier. So molality is going to be moles of solute, which in this case is the nitric acid. So 1.08 moles over kilograms of solvent. 32 grams converts to 0.0320 kilograms. And so we've got 1.08 over 0.0320 rounded to 3 sig figs is 33.8. 33.8 molal concentration. And then for the molarity, we need to get the volume of the solution. We need the volume of the solution, not just the solvent. Molality is moles of solute over kilograms of solvent. Molarity is moles of solute over liters of solution. So I guess I want to switch colors here just for the sake of contrast, but 1.08 moles over how many liters of solution do we have? So the total grams of solution is 100 based on my assumption, and that's an exact 100 for sig fig purposes. So 100 grams at a density of 1.24 grams per milliliter. I would say 100 grams times 1 milliliter over 1.24 grams gives me 80.6 milliliters. I would get 80.6 milliliters of solution. Whoops. 80.6 milliliters of solution, which converts to 0.0806 liters. 0.0806 liters of solution. And that equals, these concentrations are pretty ridiculously high. 1.08 divided by 0.0806 is about 13.4. Is about 13.4 moles per liter, or 13.4 molar. All right, there we go. So there's another one of those concentration conversion problems starting. Well, was it another one? Because I think the first one we did, they didn't start us off with a concentration. Yeah, so I guess this is really our first concentration conversion problem, starting with mole fractions. I'd like to do one starting with molality and one starting with molarity. Wait, no. We started with percent mass here. So we want to do one starting with mole fractions and one starting with molality and one starting with molarity. If we come across those as we go, then great. If not, I'll just make some up. But I would like to do an example of each case, an example of each starting point. Anyway, back to the list. So that was 31. Well, 31 plus because I added to it. 32, calculate the mole fraction of each solute and solvent. You can do that. Let's take a look at something else. Okay, what do we have on this page? Where did my note card go? Oh, there it is. So, according to my note card, which ones did I want to see from this? I guess just 34. Yeah, I see, because 33 is the same as 32. 34. So we've got a solution that's 40% methanol, 40% ethanol, and 20% water by mass. And they want us to calculate the mole fractions. Well, I guess we already did that with the previous problem. I guess we already did that with problem 30, so... Or, was it problem 30? What was the problem that we just did? Maybe it was 31. So yeah, I think we can pass on 34. 35, what is the difference between a 1 molar solution and a 1 molal solution? They both have 1 mole of solute, but one is per liter of solution and the other is per kilogram of solvent, which are not the same thing. They don't necessarily have the same mass and volume. 36, what is the molality of phosphoric acid in a solution of 14.5 grams phosphoric acid and 125 grams of water? That's basically the same as what we did for the hydrogen and palladium problem earlier, so we'll pass on this. 37, What is the molality given 68% nitric acid by mass? Oh, we already did that. We already did that exact one, 68%. Okay, good to know. Then I guess we'll need to look for something else. What about this? Calculate the molality of each of the following. You know how to do that. Convert the grams to moles and divide by the kilograms of water or whatever the solvent is. 39 is basically the same thing. Okay, pass. Number 40, the concentration of glucose in normal spinal fluid is 75 milligrams per 100 grams. Okay, so that's a different measure of concentration. What is the molality of the solution? I mean, not too hard to do. Convert your 75 milligrams of glucose to moles and then convert your 100 grams to 0.100 kilograms and you're done. 41, a 13% solution of potassium carbonate has that density. Calculate the molality. Well, we already did this with the nitric acid example. So, yeah, I think I'll pass on this. If they had us starting with something other than percent, then that would be worth doing, but we already did an example with percent mass as a starting point, so I'll leave that as an exercise for you to practice with on your own. What else do we have? 42, assuming ideal solution behavior. What's the boiling point of 115 grams of non-volatile sucrose in 350 grams of water? I don't know why they bothered to mention that sucrose is non-volatile, but okay. Is it worthwhile? I don't think so. Oh, I'll tell you why they mentioned the volatility of sucrose. So the boiling point elevation and freezing point depression equations only work for non-volatile solutes. Things that, don't naturally evaporate over time. So, yeah, I wouldn't worry about that with solid solutes to begin with. Some solid solutes are volatile, but I don't think many of them are. So, I guess that's why they're bringing it up. But if it was volatile, it's not like you would know how to deal with it, so you don't have to worry about cases where you have volatile solutes. Except maybe if they ask you, oh, somebody did an experiment and they used the same calculations you would normally use, but their solute was volatile and so their calculations were off. Explain. Well, they wouldn't mention that it was volatile, but you would offer that as an explanation. Anyway, I don't see anything worth doing in 43. I think we already did an example of boiling point elevation and freezing point depression, and it's not that hard. It's a really simple equation. 44, assuming ideal solution behavior, what's the boiling point of a solution of 9.04 grams of iodine and 75.5 grams of benzene, assuming the iodine is non-volatile? Same thing, except this time the solvent is not water, it's benzene. So if you go back to that chart, and I guess I'll pull it up for you so that you don't have to scramble for it. Where was that chart? There it is. So yeah, if you go back to this chart, you've got benzene in the third row there. There's its normal boiling point and freezing point, and its elevation and depression constants. So using that information, you can figure out the new boiling and freezing points. add the boiling point elevation to the normal boiling point, subtract the freezing point depression from the normal freezing point, and you're good to go. So there's that. I don't think we need to go over it. What about this set? So it looks like, is 45 worth our while, assuming ideal behavior? What's the freezing temp? No, it's another freezing point depression question. You know how to do it. 46, assuming ideal behavior, yeah, more of the same. 47, assuming ideal behavior, what is the osmotic pressure of an aqueous solution of 1.64 grams of calcium nitrate in water at 25 Celsius? The volume of the solution is 275 milliliters. And then it looks like 48 is similar, and 49 is, well, 49 is something different, but yeah, let's look at 47. Or actually, you know what? Let's do, should we do 48? If they, so they're asking for the osmotic, oh yeah, 48 will be easier because they actually give us the molar mass rather than us having to calculate it from the periodic table. Then again, you know what? No, let's do 47 because 47 has something important. Some of you might already notice what it is. But yeah, 47. Let's go ahead and work it out. Oh, and I haven't switched to my camera yet. There we go. So problem 47. We've got 1.64 grams of calcium nitrate. 1.64 grams of calcium nitrate. And we've got a volume of 275 milliliters. This is the volume of the solution, of course, is 275 milliliters, or 0.275 in liters. There we go. That 5 didn't look too good. And let's see, they give us a temperature of 25 Celsius. So in kelvins, that's going to be 298 kelvins after adding 273. 298 kelvins. Okay, so we need to calculate the number of moles of calcium nitrate. And for that, we need the molar mass. So calcium is about 40.08 grams per mole. 40.08 plus nitrogen is about 14.01. And I'm going to multiply that by 2. Plus oxygen is 16.00, and I'm going to multiply that by 6. Each nitrate contains 3 oxygens, and 2 nitrates would have a total of 6. So that's 164.10 grams per mole. Oh! Interesting choice of numbers. Okay, so 1.64 over 164.10 is going to be about 1%, 0.01, but let's actually calculate it. 1.64 over 164.1 is 0.009993 for 3 sig figs, I guess. Yeah. those 9s aren't going to round up. So, in fact, the number of moles is 0.00999 in keeping with 3 sig figs. So close. So close to 0.01, but not quite there. All right. Where do we go from here? I guess our equation. Osmotic pressure equals molarity times the ideal gas constant times the absolute temperature. Did they tell us in this case? No, they want us to calculate the pressure, so I'm just going to do it in atmospheres. So molarity is going to be 0.00999, the moles, over 0.275, the liters. So equals 0.00999 moles over 0.275 liters. And I guess I'll write the units, times ideal gas constant is going to be 0.08206 liter atmospheres per mole Kelvin. Times 298 kelvins. Kelvins cancel out, moles cancel out, liters cancel out, and we're left with atmospheres. Okay, so 0.00999 over 0.275 is going to be 0.0363. So that's 0.0363. And then times the ideal gas constant, so 0.0363 times 0.08206 is going to be 0.00298, it looks like. Oh, more interesting results. 0.00298. 298, huh? And then times 298 kelvins. So 0.00298 times 298 rounds to 0.888. Okay, so about 0.888 atmospheres worth of osmotic pressure. There we go. Or at least you would think that's the end of it, except, what am I forgetting? I'm forgetting my Van't Hoff factor. So our Van't Hoff factor is, in this case, going to be 3. Calcium nitrate splits up into a calcium ion and 2 nitrate ions, so I should multiply this by 3. And if I do that, then I get 0.888 times 3 is about 2.66. 2.66 atmospheres. And there we go. Now, you could argue that students wouldn't forget it if they just wrote down the equation because the I is already in the equation, except it's not. Most instructors and most textbooks don't include the I in the equation until, again, like I mentioned before, they add it on towards the end of the chapter. So you might just be given the equation without the Van't Hoff factor in it, and you'll just be expected to remember it, which is, I don't know what their deal is, but that's the way they do it. So Yeah, you really do have to remember to add in the I, because most formula sheets I've seen out there and most textbooks don't present the equations with the I's included. So there's that. Yeah, 48 is basically the same thing, but it involves insulin, which you can consider to be a non-electrolyte, so a Van't Hoff factor of 1. So we'll skip 48. Is 49 of any interest? In assuming ideal solution behavior, what's the molar mass of a solution of 5 grams of a compound and 25 grams of carbon tetrachloride? And they give you the boiling point and elevation constant. Oh, okay, this is a little different. So yeah, you can use boiling point elevation to calculate molar mass, interestingly enough. It's not too hard to do. I think I'll just set it up. But yeah, let's do this one. Or at least give the setup for it. Okay, that's looking better. So we have 5 grams of a compound. They don't tell us what it is, but 5.00 grams of X. And 25 grams of carbon tetrachloride. So that's carbon and 4 chlorines, CCl4. Okay. And the boiling point is normally 76.8, so BP is normally 76.8. Or no. Hold on. That's not the normal boiling point, is it? Is carbon tetrachloride on our list? I think it might be. Okay, that's chloroform. Right. Okay, yeah, that must... Okay, whatever I said about chloroform earlier then was probably wrong. Okay, yeah, chloroform is another name for carbon tetrachloride. I was second guessing myself earlier for no reason. Yeah, CCl4, it is chloroform. So its normal boiling point is 61.26 degrees Celsius. Something worth remembering. So this is the elevated boiling point, and the normal boiling point is 61.26. I guess I'll just round it to 61.3 degrees Celsius. And you know this one's the normal boiling point because it's the lower one. I guess I'll just add the word normal to be on the safe side. Normal boiling point is 61.3. Okay. And then what did the problem say? So... No, hold on. No. 76.8 is the normal boiling point of carbon tetrachloride. Okay. I'm going to need to double check what chloroform is. Okay, this is wrong. So yeah, they actually did give us the normal boiling point and the elevated boiling point. Okay, I'm overthinking this, and I need to double check my organic nomenclature. For some reason, my brain is just malfunctioning today. So normal boiling point is 76.8, and in the problem it said that the new boiling point is 81.5. 81.5 degrees Celsius is the elevated boiling point. And they gave us the boiling elevation constant is 5.02. K boiling is 5.02 Celsius degrees per unit of molality. Okay. I think that's everything we need then. So, of course, we are assuming here that this mystery compound is a non-electrolyte, which is a very reasonable assumption because if it's dissolved in carbon tetrachloride, which is nonpolar, then this thing is probably nonpolar, which would mean it's definitely not ionic. So a very reasonable assumption is that it is a non-electrolyte, will not dissociate, and was I really going to write 0 there? The Van't Hoff factor is equal to 1. Van't Hoff factors of less than 1 are unrealistic. Okay, so we don't know what X is, but we do know that whatever the molar mass of X is, I can take 5.00 grams divided by the molar mass of X would equal the moles of X. And then I can take the moles of X divided by the kilograms of solvent, kilograms of CCl4, so that's going to be, let's see, 0.025, yeah, 0.025, not 00, 0.025, and then 2 zeros at the end there. That's going to be the molality of X. And then the change in boiling point, the boiling point elevation, is going to be equal to Kb times the molality of X times I, which is going to be 1 in this case. So what's the boiling point change? 81.5 minus 76.8 is, let's see, 81.5 minus 76.8. I feel like I should be able to do this without a calculator, but whatever. 4.7. So we've got 4.7 equals 5.02 times, well, we don't know yet, times 1 for the Van't Hoff factor. Divide by 5.02, you've got the molality. Whoops, 4.7 over 5.02 is about 0.94. So we're getting 0.94 here. And then 0.94 times 0.025 is going to give us about 0.024. Okay, so that tells me that the number of moles, and let me switch colors here, that the number of moles is about 0.024 moles. And if we have 0.024 moles and 5 grams of the stuff, then the grams per mole, 5 grams divided by 0.024 gives us the molar mass. 5.00 divided by 0.024 is about 208.33. Of course, rounding to 2 sig figs, we would just say that's a molar mass of 210. So the molar mass of our unknown substance is 210 grams per mole. And there we have it. Okay. What else do we have on this page? We just did 49, 50, a sample of an organic compound, which is a non-electrolyte, weighing 1.35 grams, lowered the freezing point of 10 grams of benzene by 3.66, assuming ideal solution behavior, calculate molar mass. Okay, we just did an example of that, so there's one that you can try out on your own. What else do we have? We're getting closer to the end of this problems list. 51, a 1 mol solution of HCl, or hydrochloric acid, in benzene has a freezing point of 0.4. Is HCl an electrolyte in benzene? So we talked about this earlier. Benzene is nonpolar. It's not going to really separate the hydrogen ions from the chloride ions. So in this case, for problem 51, the Van't Hoff factor for hydrochloric acid is 1, not 2. If it was in water, it would be 2, but in this case it's 1. Other than that, it's a pretty standard problem. Well, actually, is there even a problem here? No, it's just a conceptual question. It's just a conceptual question, and I guess you can do some calculations to justify what I just said. If you take into account the freezing point depression constant of benzene, let me look that up. So the freezing point depression constant of benzene is 5.12. And the normal freezing point of benzene... Wait, that doesn't... Yeah, that's right. Because if the normal freezing point of benzene is 5.5, then, and the freezing point depression constant is 5.12, then you've got 1.0 molal times 5.12 times a Van't Hoff factor of 1 would be a delta T freezing of 5.1. And if you subtract that from 5.5, you do get 0.4. Okay, so I basically just worked out the whole problem for you there. So yeah, the fact that we get a freezing point of 0.4 when you assume that I equals 1 just further proves it. Okay, do we need to look at 52? A solution contains 5 grams of urea, a non-volatile compound, dissolved in 0.1 kilograms of water. If the vapor pressure of pure water is 25 degrees Celsius, or at 25 degrees Celsius, is 23.7 torrs, what is the vapor pressure of the solution, assuming ideal solution behavior? So we did go over how to use Raoult's law. I guess here's an example with real numbers that we can work with. So the pressure is 23.7, get the mole fraction of the water. So you'd have to convert your kilograms of water to grams and convert the grams of water to moles. Also convert the grams of urea to moles. And then take the moles of water over the moles of water plus urea, multiply by the 23.7, and you'll get the new vapor pressure according to Raoult's law. We already showed an example of using Raoult's law, albeit a very simple one, but I think you have enough background on this to be able to do it on your own. 53. Calculate molar mass. We already did something like that. 54. Arrange the following solutions in order by their decreasing freezing points. And I'm assuming they all use the same solvent, whether it's water or something else, but okay, so 0.1 molal sodium phosphate, 0.1 molal ethanol, 0.1 molal carbon dioxide, 0.15 molal sodium chloride, and 0.2 molal calcium chloride. So what they're getting at there is the role of the Van't Hoff factor. So the Kf in your freezing point depression equation is going to be the same for all of these. What's going to be different is the m and the I. So the m times I is your basis of comparison. Did I say comparison? Comparison. Like I said earlier, I can't talk today. So yeah, it's really not that hard to do. For the first one, 0.1 times 4, because sodium phosphate would give you 3 sodium ions and 1 phosphate ion. So 0.1 times 4 is 0.4. The ethanol is just going to stay as 0.1 times 1. The carbon dioxide is 0.01 times 1. The sodium chloride is 0.15 times 2. You get 1 sodium and 1 chloride. And the calcium chloride is going to be 0.2 times 3. You get 1 calcium and 2 chlorides. So 0.2 times 3. And yeah, just rank them. The lowest freezing point is going to be, I guess, calcium chloride, because 0.2 times 3 is 0.6. Then it looks like sodium phosphate, because 0.1 times 4 is 0.4. Then sodium chloride, 0.15 times 2 is 0.3. Then the ethanol is at 0.1. Then the carbon dioxide is at 0.01. So that's from lowest to highest freezing points. 55, I think, is pretty similar. Let's see. Yeah, 55 seems to be pretty similar, except they don't want you to rank them, they just want you to actually calculate the delta T B. Okay, 56. Is 56 noteworthy? How could you prepare a 3.08 mole aqueous solution of glycerin? Oh, wow. I would think they would have put this problem a little earlier on, because it's a pretty simple problem. They're just asking you, like, what would you do in the lab? Of course, you would measure out the correct number of moles, and you'd weigh an appropriate amount of water, and you'd just mix them, and you're done. So yeah, get 1 kilogram of water and 3.08 moles of glycerin, however many grams that is, and you're done. 57, a sample of sulfur weighing 0.210 grams was dissolved in 17.8 grams of carbon disulfide, whose boiling point elevation constant is given as 2.43. If the boiling point elevation was 0.107 degrees Celsius, what is the formula of a sulfur molecule in carbon disulfide, assuming ideal solution behavior? Oh yeah, natural sulfur actually exists as a molecule, as a bunch of sulfur atoms connected to each other. But yeah, you can do this on your own pretty easily. Get the molar mass. Because, yeah, they give you the grams of sulfur, but not the moles, and you can calculate the moles just like we did with that other problem where we were asked to get the molar mass of some unknown substance X. And yeah, once you get the molar mass, you're going to notice it's not equal to the molar mass of sulfur on the periodic table. If you divide by the molar mass of sulfur, you'll see that it's approximately a whole number of sulfur atoms. If I'm not mistaken, the number you're supposed to get is 8. But yeah, we can skip that one. You can do it on your own. 58. Is 58 worthwhile? So cadmium iodide in water, raise the boiling point. What does this suggest about the nature of a solution of cadmium iodide? Okay, so for this, basically they're asking you to solve for the Van Hoff factor and measure the degree to which cadmium iodide will dissociate. Will it completely separate, or will it only partially separate? If it completely separates, you'll get 3. If partially, then you'll get less than 3. 59. Let's see, we've got an enzyme that cleaves cell walls, and they give you the osmotic pressure and they want you to calculate the molar mass. Okay, just use the osmotic pressure equation and work backwards from there. You can assume that this enzyme has a Van Hoff factor of 1. And yeah, it's really not that hard to do. 60. They give you the osmotic pressure of a solution containing 7 grams of insulin per liter at 23 torrs at 25 Celsius, assuming ideal solution behavior. What's the molar mass of insulin? Okay, so kind of like the other molar mass question we did with boiling point elevation, you would use the osmotic pressure equation with the pressure and temperature given to calculate the molarity, and then assume you've got 1 liter of solution and multiply by the molarity to get the moles, and then take your 7 grams divided by that number of moles, and there's your molar mass. So not too different from what we did with boiling points. You're just starting with a different equation. Okay. What about this set? Let's see, 61. You can do on your own, that's not too bad. 62. So oh, okay, interesting. So they give you the boiling point, and from that you can compare it to the normal boiling point of benzene to calculate the boiling point elevation, and then you can work backwards from there to figure out the molality, which you can then plug into the freezing point depression equation. Okay, it's not that horrible. You can do it. 63. 63 is basically the reverse of 62, where they give you the new freezing point and you have to work backwards to get the molality and then get the new boiling point. Not all that bad. In fact, not only would you get the molality, you'd get the molality times the Van Hoff factor. You'd get the M times I. So even if you didn't know what the compound was that was dissolved in there, you'd still be able to answer questions 62 and 63 without that knowledge. 64. The sugar fructose contains 40% carbon, 6.7% hydrogen, and 53.3% oxygen by mass. Solution of fructose and ethanol has that boiling point. What is the molecular formula of fructose? Oh, okay. So what they're doing there is you start with the percents by mass. We did this a long time ago. I think it was like video number 2 or 3. Empirical formulas versus molecular formulas. So you use those percents they gave you to get the empirical formula, and you use the boiling point elevation equation to get the molar mass, and then the molar mass of the actual molecule versus the molar mass of the empirical formula. You should get a whole number ratio between them, and yeah, you can get the molecular formula out of that. If you don't remember that stuff, then go back to, it was either video number 2 or video number 3, where we discussed empirical formulas. Okay, what about 65? Vapor pressure of methanol versus the vapor pressure of ethanol at the same temperature. Calculate mole fractions. Calculate vapor pressure. And calculate the mole fraction. Okay, we already talked about how to do this. So if you've got two liquids dissolved in each other, then to calculate the vapor pressure, you just take the normal vapor pressure times the mole fraction for each individual part of the solution, and you add them all up to get the total vapor pressure. Nothing too hard there. We're getting close to our last set of problems here, and it looks like I am actually going to have to make up some concentration conversion problems. So let's see, 66 says the triple point of air-free water is defined as 273.16 kelvins. Why is it important that the water be free of air? Because if you have air dissolved in there, then that's going to affect the boiling point and freezing point and all that. And the triple point is the point where the solid, liquid, and gas phases are all in equilibrium, so I would imagine that would have to have some sort of effect. But I guess you could just say, in general, if you want to keep it vague, having air dissolved in there is going to affect the physical properties of the water. 67. Meat can be classified as fresh even though it is stored at -1 degrees Celsius. Why wouldn't meat freeze at this temperature? Because the water in the meat is exposed to, well, everything else that's in the meat, the salts and stuff. So yeah, its freezing point is not going to be at 0 Celsius, it's going to be at lower than 0 Celsius. So even at -1 Celsius, the meat will probably still not be frozen. Or the water content of the meat will not turn to ice. That being said, I would be curious to hear what Gordon Ramsay has to say about that. Anyway, moving on, 68. An organic compound has that percent composition. Okay, that's another molecular versus empirical formulas, a callback to one of the earliest chapters we covered, so there's that for those of you who feel like you need a refresher on it, or you want to check how well you remember it. 69. Testing whether or not it's an electrolyte, so solving for the Van't Hoff factor. We already described problems like this. 70. Let's see. So they want you to figure out the formula of the mystery salt. This is interesting. And they don't tell you what the salt is, but you can figure it out because you can figure out its molar mass and then just pick the appropriate metal. They did say it's an alkali metal, so it must be lithium, sodium, potassium, rubidium, cesium, or francium together with fluorine. So, yeah, do what we did with that other molar mass problem. And once you get the molar mass, subtract out the fluorine, and you should get the molar mass of whichever alkali metal the fluorine was paired with. And that's the end of that. Okay. Well, I guess that's pretty much it for problems. So I want to make up my own problems for concentration conversions because a lot of students struggle with concentration conversions. We already did from percent mass to mole fraction, molality, and molarity. I want to do the other three, so let's say I have a solution of, let's say I have a solution of glucose whose molar mass is approximately 180 grams per mole. Let's just say it's 180 for our purposes. So a solution of glucose, which is 180 grams per mole, dissolved in water, has the mole fraction of glucose, a mole fraction of, I'll just abbreviate it, gluc, as 0.0250. Find its molality. Whoops, that's not how you spell find. Find its molality, molarity, and percent glucose. And let's say it has a density of, let me just make something up here. Let's say the solution has a density of 1.08 grams per milliliter. Okay, so when we started with percent mass, we made an assumption. We assumed that we had 100 grams, which isn't a foreign concept to you if you remember how we dealt with empirical formulas when we were given percent masses. Assuming you have 100 grams just makes it convenient because you can directly convert the percents to grams. But this time we're starting with a mole fraction, so what should we use for our assumed amount? Since mole fraction deals with moles, I'm going to assume we have 100 moles of solution. So I'm going to assume that I have 100 moles of solution. And if I make that assumption, then based on this mole fraction, I know that my total moles of glucose would be, let's see, 0.0250 equals moles of glucose over moles of solution, so 0.025 times 100 would give me 2.50 moles of glucose. And the rest would be water, so that would be 97.50 moles of H2O. All right, and now we can get started with finding the other concentrations. So, as for the percent glucose, I think I want to start with that first. I would need to get the masses. I would need to get the total mass of the solution and the mass of the glucose. Easily done, so 2.5 moles of glucose, if you multiply by 180, 2.50 times 180 gives me 450 grams of glucose. I'll include a decimal point there to show that it still has 3 sig figs. So that's 450 grams. And then for the water, it's going to be a molar mass of 18.02. So 97.50 moles times 18.02 grams for every 1 mole. Rounding to 4 sig figs, that's 1757 grams. 1757 grams. And because I know I'm going to need it in kilograms later, I'll go ahead and say that's 1.757 kilograms of water. Okay, so the total mass of the solution is 450 plus 1757, which is 450 plus 1757 is 2207 grams. So we've got 2207 grams of solution, which we can use right now for the percent glucose, and we'll use it later when converting to volume of solution. So 450 grams over 2207 grams in total. 450 divided by 2207, and then times 100% is going to be, let's see, with 3 sig figs, that's 20.4%. So I'm getting 20.4%. Okay, we can get molality pretty easily. 2.50 moles over 1.757 kilograms. So 2.50 moles over 1.757 kilograms is going to equal 2.50 over 1.757 is about 1.42 molals, or 1.42 moles per kilogram. Okay, and for molarity, we need the volume of the solution in the denominator, which means we need to use the grams of the whole solution to convert with the density. So 2207 grams of solution, every 1.08 grams of solution is 1 milliliter of solution, so 2207 over 1.08 is 2044, actually 2040 since we need to round it to 3 sig figs, 2040 milliliters, and converting to liters, that's going to be 2.04 liters, 3 sig figs. Okay, and last but not least, we can now calculate the molarity. So 2.50 moles of glucose over 2.04 liters of solution is going to give us a molarity of 2.5 over 2.04, 1.23, about 1.23 molar, or 1.23 moles per liter. And there we go. So that's starting from mole fractions. Just assume you've got 100 moles of solution, and the math will be pretty easy from there. Of course, if you don't like 100 and you like torture, you can assume 243 moles of solution, or whatever number you like, but 100 is the most convenient, at least in my opinion. Okay, next, let's do one where we start with the molarity and we need to get everything else. So let's say we have, what should I use? I'm not even sure. I want a compound whose molar mass is easily calculated. Maybe I should stick with glucose after all. Or you know what? Hydrochloric acid isn't too hard to figure out. Yeah, let's do a 1.50 molar HCl solution has a density of, let's make it 1.32 grams per milliliter. I'm making up these densities like I stated earlier. So don't quote me on these densities. Find, I forgot my period there, find, well, the molality, the percent mass, and the percent HCl, and the mole fraction of HCl. Okay. So in this case, what you want to do is assume you've got 1 liter of solution. 1.50 molar is 1.50 moles per liter, so assume you have 1 liter of solution, not 1 liter of water, 1 liter of solution. From that assumption, we can conclude that we've got 1.50 moles of HCl. By the way, let me get its molar mass. So 1.01 plus 35.45 is 36.46. 36.46. Where should I write it? I guess up here. 36.46 grams per mole is the molar mass of hydrochloric acid. Okay, so let's see. It means we've got 1.50 moles of hydrochloric acid, and it also means we've got 1 liter or 1,000 milliliters of solution. Okay, if we have 1,000 milliliters of solution, then I can figure out how many grams of solution I have. I've got the density, so if I multiply by 1.32 grams for every milliliter, that's supposed to be a 1 milliliter, then let's see, milliliters cancel and I get 1,000 times 1.32 would be 1,320 grams of solution, 3 sig figs. So maybe we should write it as 1.32 times 10 to the 3 grams of solution. Okay, but that's the grams of water plus hydrochloric acid. So we need to separate those from each other because for molality, we need the mass of just water. And also for the mole fraction, we would need the mass of just water because we need to calculate the moles of just water. So that we can add it to the moles of hydrochloric acid, but yeah, we'll get to all that stuff when we get to it. So let's start with getting our grams of HCl. 1.50 times 36.46. Rounding to 3 sig figs, this is going to be 54.7 grams. Okay, and if we've got 1320 grams minus 54.7 grams, then that's 1265.3 grams of water, which I would have to round to 1270, I guess. So we've got 1.27 times 10 to the 3 grams of H2O. Okay, let's see. So with this, I can go ahead and actually calculate percent mass. 54.7 over 1320 times 100%. 54.7 divided by the grams of the whole thing, so 1320 times 100%. It was 3 sig figs over 3 sig figs, so 3 sig figs. It's going to be 4.14%. Okay, for molality, I can calculate that as well now that I know the mass of the water. 1.27 times 10 to the 3 grams of water is the same as 1.27 kilograms of water. And now that I know the kilograms of my solvent, 1.5 moles over 1.27 kilograms, 1.50 over 1.27 gives us a little over 1.50 over 1.27 is about 1.18 moles per kilogram or molal. Okay. Next we've got mole fraction. So we already know the moles of HCl. We need the moles of water. If you've got 1.27 times 10 to the 3 grams of water, how many moles is that? Water is 18.02 grams per mole, so 1270 grams divided by 18.02, rounding to 3 sig figs, is 70.5 moles. So we have 70.5 moles of H2O. And now we can get the total moles, 70.5 plus 1.5 is going to just be 72, and the mole fraction is 1.50 over 72.0, which equals 0.0208. After rounding to 3 sig figs, 0.0208. All right, and that's starting from molarity. Last but not least, we want to do one starting with molality. So let's see. Yeah, I'll just use HCl again. So let's say, oh, how about we use the same number just so we can compare and contrast? Yeah, let's say we've got a 1.5 molal HCl solution. And let's say it has a density, let's keep the same density of 1.32. Has a density of 1.32 grams per milliliter. Okay, and don't forget the period there. Find everything else. Find molarity, mole fraction of HCl, and percent HCl by mass. All right. So in this case, what do we want to assume we have? If you've been following the pattern with the other three cases, your assumption should really just be based on whatever's in the denominator of the concentration units that you were given. Molality is in moles per kilogram of solvent, so I'm going to assume 1 kilogram of solvent. In 1 kilogram of solvent, that assumption gives us 1.50 moles of hydrochloric acid, and it also gives us 1 kilogram or 1,000 grams of H2O. All right, so let's see. I guess we can start by getting grams of HCl. 1.5 moles of HCl is 54.7 grams. Okay, now I'm really glad I reused HCl. So 54.7 grams. All right, so now that I've got this, I can get the total grams. And this 1,000 grams was based on my assumption of 1 kilogram, my assumption of exactly 1 kilogram, so I could say this is 1,000.0 plus 54.7 is 1,054.7. So yeah, my total solution is going to be 1,054.7 grams. And I can use that to calculate percent mass. 54.7 over 1,054.7 is that number times 100% is 5.19, if I round to 3 sig figs, 5.19%. Okay. Next up, I can, well, if I have my grams of solution, I can get the volume of my solution. Or I could go for the mole fraction next. So I could go either way. Let's go for molarity. So 1054.7 times 1 milliliter for every 1.32 grams gives us how many milliliters? 1054.7 divided by 1.32, rounded to 3 sig figs, is 799. So that's 799 milliliters, or 0.799 liters of solution. And moles of solute over liters of solution gives me my molarity. So that's 1.50 over 0.799 equals 1.50 over 0.799. That's 1.88. 1.88 moles per liter, or molar. Okay, and finally mole fraction. So I already have my moles of HCl. I need to get my moles of water. 1,000 grams of water with a molar mass of 18.02. That's going to be 1,000 grams times 1 mole over 18.02 grams. And that's going to be 55.49. 55.49 moles. Okay, and my total moles then would be 1.50 plus that, so total moles is 56.99 moles of solution. And 1.50 over 56.99 rounded to 3 sig figs would be 0.0263. 0.0263. And of course, mole fractions have no units. And there we go. So that's all of the possible concentration conversions. We've got one last thing to talk about before we wrap things up. It's kind of an FYI topic. You don't really need to pay that much attention to it. I mean, if it's, you know, the last hour before the exam and you're scrambling for something to review, I would not pick this topic because it's not the most crucial. You might get a couple of obligatory questions on it. But yeah, our next topic is the topic of colloids and suspensions. So really more of a conceptual topic than anything else. Colloids and suspensions. Colloids and suspensions are heterogeneous mixtures. They're not solutions. Colloids, you can easily mistake them for solutions more easily than suspensions. With suspensions, it's a little bit more obvious that they're not solutions, but you know, there's all kinds of both, so you never know what you might encounter. So let me see, do I have any visuals ready for this? Well, just one thing about a property that colloids have. But yeah, colloids can form with basically any combination of phases except for gas with gas. When you mix gases with other gases, you always get a solution. But for everything else, you can pretty much put together whatever combinations you want, and I guess here's a chart that actually lists a bunch of them. So yeah, there you go. Colloids are basically what happens when you're trying to dissolve something, but the particles are just too big to dissolve. Not so big that they don't disperse within the solvent, but too big to actually fully break apart on a molecular level. So those are some examples where the dispersed phase also, you can think of it as the solute-like phase, the thing that's kind of like a solute, but not quite. And the dispersion medium, which is kind of like a solvent, except it's technically not because you're not making a solution. So dispersed phase and dispersion medium, you can call them solute-like and solvent-like if you prefer. But yeah, solid and gas, solid and liquid, solid and solid, liquid and gas, liquid and liquid, liquid and solid, gas and liquid, gas and solid, but you do not have gas in gas. All gas and gas mixtures are homogeneous mixtures, so you can't make gas in gas colloids. But yeah, those are some typical examples. You can read through the chart for yourself. Some of these combinations have special names, so solids and liquids are called sols. Liquids and gases are called aerosols. You've probably heard that term before, especially around workshops that, you know, deal with paint and stuff like that. Another term you might have heard around workshops? No, hardware stores. Another term you might have heard around hardware stores is emulsions, liquids and liquids. So milk, mayonnaise, butter, and various types of paints. And yeah, there you go. So they're all heterogeneous mixtures, yet they feel like homogeneous mixtures. And given some of those examples, I think you can sort of see that. Milk feels like it should be homogeneous, but it's not. On a microscopic level, you can tell that it isn't. And yeah, that's really all there is to it. They're not all that interesting. Well, there is one interesting thing that they can do. So colloids are actually able to exhibit something known as the Tyndall effect, which you've probably seen in real life plenty of times. Here's one picture that they use to illustrate it, but if you Google the Tyndall effect, you'll find, you know, more natural displays of this phenomenon. The Tyndall effect basically is the result of light bouncing off of these particles that aren't quite dissolved. So in this case, you've got the Tyndall effect due to light bouncing off of dust particles in the air or smoke or something like that. And that's why you can see the path of those beams of light. It's because some of the light is actually bouncing sideways from the path of the beam to your eyes. And you've probably seen this if you have a bathroom with a window and you take a shower when it's daylight and the sun is facing your window, then you can probably see when there's a lot of steam, you can see like the beams of sunlight going through. That's also the Tyndall effect. You can also see the Tyndall effect in liquids, maybe not in milk, but a more colored liquid. If you shine a flashlight beside a glass of some liquid colloid, then you will notice the light scattering there as well. And yeah, that's basically it for colloids. That's the essentials of what you need to know as far as a general chemistry course is concerned. What about suspensions? So suspensions are not going to do what colloids do. With suspensions, the particles are just bigger. Way, way bigger. With suspensions, the particles are just that much bigger and they don't dissolve, and usually you can notice like sizable chunks of material within whatever the solvent-like substance may be. And I think that's all I have to say about it, really. Yeah, there you go. I don't know why I dedicated an entire sheet to this, but that's colloids and suspensions for you. Really just sort of an FYI topic for this chapter. I think they have, a couple of conceptual questions here that you can spend some time thinking about. Identify the dispersed phase and the dispersion medium in each of the following colloidal systems. You can just Google around these answers. You can just do some Googling to figure it out. Or I think some of these are actually mentioned in the chart I had up earlier. But again, it's not the most important thing to know about. Distinguish between dispersion methods and condensation methods for preparing colloidal systems. That's stuff you can read about in a textbook, or just Google how colloids are made. How do colloids differ from solutions with regard to dispersed particle size and homogeneity? Homogeneity kind of equal, but dispersed particle size for colloids is bigger, noticeably bigger. Explain the cleansing action of soap. That has nothing to do with colloids, at least as far as I'm aware, but the reason soap works the way it does, this ties back into the whole like dissolves like idea. So with soap, the soap molecules are actually specially engineered to have like a polar part, and a non-polar part. And usually the non-polar part is really big compared to the polar part. It's usually a long chain of carbons with maybe some additional stuff attached. But yeah, that's the non-polar part. And the idea with how soap works is, well, soap is supposed to be able to dissolve the stuff that you want to get off of your hands if you're washing your hands with soap, or get, bits of food off of your pots and pans and dishes when you're washing the dishes. So, since some of those things are more oily and nonpolar, you need soap to have a nonpolar part to it that can attract and dissolve with the nonpolar junk that you're trying to clean. And you might also have some polar contaminants that you want to get rid of, so that's where the polar end comes in. And the other role of the polar part is to allow the soap to dissolve in water in the first place, so that you can actually wash it off when you're done. And yeah, typically what will happen is that the nonpolar parts will gather around some sort of polar oily substance that you want to wash off. So let's say here's some sort of fat or oil that you're washing off of the dishes, and so you'll have the nonpolar parts will kind of just gather around it like this. So those are the nonpolar parts, just kind of surrounding some sort of nonpolar thing you're trying to dissolve. And eventually what you end up with is it kind of just balls up. It turns into this ball where the exposed outside parts are just the polar parts, which can dissolve in water. So Those polar parts then just get surrounded by water molecules. I'm not going to draw the lone pairs just to save time. But yeah, the water molecules, I just said I wasn't going to draw the lone pairs. But yeah, the water molecules can start surrounding the polar parts, and then the whole thing just gets washed down the drain with the rest of the water. And that's basically how soap works. So basically it incorporates the best of both worlds. It's got polar parts to dissolve polar stuff and non-polar parts to dissolve non-polar stuff. I mean, it's probably more designed for the non-polar stuff because the polar junk that's on your hands, you could just wash that off with plain water, right? You can just wash it off with regular water. You wouldn't need soap if all the stuff on your skin or on your dishes was polar to begin with. Water would be enough. Anyway, that's the cleansing action of soap. More FYI stuff, but there it is. 75, how can it be demonstrated that colloidal particles are electrically charged? This is something that you're probably better off Googling, but if you have charged colloidal particles, the example that comes to my mind is those cleansing filters for factories so that they don't emit a lot of smog. They charge up the dust particles and then they make the smoke and dust go up through a tube that has like electrically charged elements, and the dust kind of just gathers on the surface of those charged pieces. And once everything is done and the factory shuts down for the day, or whatever factories do, they just kind of shake off the dust. They pound these elements with a hammer or something like that. They probably don't actually use a hammer, but you know, they hit these metal pieces that have all this dust now sticking to them, and they shake off the dust. It gathers in the bottom, and then they just, you know, they throw it out or they do something with it. But yeah, that's the one example that comes to my mind when it comes to charging colloidal particles, but you may want to read through your textbook or do some Googling around if you're interested in knowing more. But it's not the most crucial thing to know, so don't feel like you have to, only if you're curious. And yeah, I think that is it for our deep dive in solutions. We talked about solutions a long time ago in video number 4, and here we just took a closer look at solutions and how they work. And after this point, the math is going to get harder. So next time we will be covering the topic of kinetics, how quickly chemical reactions can proceed, and all that good stuff. I hope you remember your laws of exponents and things like that, because that's coming up next. The math is going to get harder from here on out. Exponential equations, logarithmic equations. If you don't remember exponents and logarithms, the time to review is now. But yeah, that's what's coming up. This has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I will see you in the next video.